Tomáš, nemůžeš prosím zavřít dveře.
Počkej, ještě nejvíc. Proč se lidi takhle to musí dělat? OK, tak to zavírám. Tak to přepni jenom na ten. Hello everybody, welcome to the session on batch processing pipelines in OpenShift with Tekton. And enjoy the show. You have to work.
Thank you. Hello, good morning. Welcome to the presentation about batch processing pipeline in OpenShift with Tekton. My name is Martin Bačovský. I work for Red Hat. I work in Connected Customer Experience team, and I would like to share with you how we process data from OpenShift in OpenShift. So, first of all, what we do. OpenShift clusters that are subscribed to the Insights program send some health data to Red Hat. Then it is processed and analyzed, and the results are returned back to the customers in form of some recommendations on how to fix or update their environments to prevent or fix issues that they might be experiencing. Also use the data internally, process them further, and we use them, for example, in OpenShift engineering to improve the product, or also we use the data in various support groups to help customers to fix their problems more efficiently. I will talk just about the processing for the internal use. The rest of the whole process, which is basically owned by the Connected Customer Experience team. If you are interested in the other parts, you might visit other talks by my fellow colleagues on this conference, and you'll definitely learn more about the whole process and the whole setup. While this is talk about data processing, I also like to introduce our data. So on Ingress, we get the health data from the clusters. We get about 250,000 archives per day. The archives are basically a tarball of some files, mostly JSON, and we receive those on Ingress. Then we process that, and the results are stored in our data lake, where we have more than 100 tables, and we produce more than 100 million of rows every day. It's actually a lot more because we process some data multiple times, but yeah, you get like the rough understanding of the amount of data that we deal with. Also, besides the data lake, data that are used for further analysis, we also have some dashboards that we develop and maintain, where we surface the data for various groups within Red Hat, and we try to provide the data in some comprehensive way so that they can use it right away. Okay, so this is time for my questions. So I would like to ask first who has some or has no experience with data processing or pipelines. Okay, thank you. Does anybody use Tekton in their? Okay, yes. And yeah, thank you. And the last question is there any Tekton contributor in here? Somebody who develops Tekton? Okay. Thank you. So let's go on. The mandatory agenda. I don't want to cover the basic things that are covered by the usual tutorials. I would like to focus more on the things that are often not mentioned in the tutorials, and that's how you should structure your pipeline and tasks so that is easy to maintain and sustainable for a day-to-day business. So we'll cover some basic topics that will be needed for the talk. We also take some information about Tekton, and the rest of the talk will be what we do to build sustainable pipelines for the job that we do. Okay, so the first thing that should be clarified is the kinds of pipelines. So there are two basic types of data processing pipelines, and as I will be talking just about the batch pipelines, I would like to explain the difference between the two approaches. So there are streaming pipelines, where the strategy is that it's built around messaging. There are some workers that are running as a like for the whole time. They are listening in the messaging queues, and the processing of the data is triggered by the incoming data, the incoming message. Basically, the workers usually process single entity at a time. They don't see the bigger scope, and the messaging is what glues the workers together. Basically, the workers take the message, process it, and the result put to another queue or store it somewhere. This is great architecture for real-time processing, usually on the ingress of data where you have the data incoming and you need to process as it comes. This is the right architecture for the job. The second type of pipelines, that's the one that we will talk about, and that's the one that we use for the data processing in my team, is batch pipelines. The architecture is a bit different. It's built around pipeline manager, which has basically description of the pipelines. Pipeline is series of tasks that have some defined order of execution, and the pipeline manager knows how to process in which order and how to process the tasks. The pipeline is triggered usually by some event. Often it is time-based. For example, we use scheduled runs of pipelines, and the task inside the pipeline runs just for the time when it processes the data. So the pipeline manager then shuts down the task and runs something else. The tasks have access to the data lake and usually process the data sets as a whole. This is great architecture when you need to process data, do some aggregations, build reports in like multiple steps. So this is what you should use. So a bit more about pipeline managers. Pipeline manager is basically the heart of the batch processing pipeline, and its job is to manage the tasks, to run in the right order, to solve the concurrency between the tasks, and so on. There is really a lot of solution on the market. There is plenty of solutions that are open source, and they differ in many things. They differ in platforms which they integrate with. They differ in the complexity of the tool. Some of the managers are really lightweight and just orchestrate the pipeline description. Some are really complex and are the full framework that helps you with creating the pipelines, often visually and so on. So on the bottom side there is a list of some well-known pipeline managers. The most often used are Airflow, Argo CD or Argo Workflows, Tekton, Jenkins. You probably know some of these. Okay, so why I will talk about Tekton. So as a data engineer, usually don't have the choice of your tools for two reasons. One is that when you are processing big data, the tooling is expensive to maintain, and companies usually have some tools already hosted or bought, or there are some available solutions. So you basically pick what there is available in your environment. The second reason is that the other option would be to run the tools on your own, and data engineers usually don't have the skills to run like such complex tools in production quality, and they also don't have the time because they focus on the data, on the tools. And that's a situation where we are. We currently operate our pipelines on Argo workflows, and it's a self-maintained system. It was not easy to set up with our skill set that we have in the team, but it works just fine. Now we are in a challenge that we need to replicate our environment to multiple namespaces in the cluster, and it's not trivial to set up for us and maintain multiple Argo instances. At the same time, we noticed that in the namespaces that we use in the OpenShift cluster, we have OpenShift pipelines pre-installed. OpenShift pipelines is basically branded Tecton, provided with OpenShift. So we were thinking if Tecton could be the tool that we switch to, because it's provided to us and it's maintained by somebody else, and that could be a solution for a problem with the workflow managers. So a few facts about Tecton. Tecton is Kubernetes native. That's the most important. We want the manager to be stable and run smoothly in an OpenShift environment. So this is satisfied. It's open source. That's great. There is also well-established open source community, because the Tecton project is there since 2018, if I'm not mistaken. So there is a lot of experience. The project has excellent documentation, so it's easy to get started. It's not very complex, and yeah, it looks like it could be the job, the tool for the job. Just to clarify the vocabulary that's used in Tecton, they have pipelines, which is the pipeline. It's composed of tasks. Every task maps to an OpenShift pod. So what's task runs on single pod in the cluster. That's important to understand. And the tasks are composed of steps, and every step is mapped to a container. So you can have multiple containers within the pod, and you can define your tasks with this kind of structure. What we were looking for the common use cases for Tecton on the internet, and they present themselves as a solution for CI/CD. So CI/CD pipelines are the most common pipelines run with the tool. The above diagram is basically typical structure of CI/CD pipeline. Often Tecton is also used for machine learning, for the training of the models, and that's the bottom diagram. That's usually linear, one task after another. The question that was ahead of us was if Tecton would work with our pipelines. So this is basically our daily pipeline, not the whole one. It's just part of it, but you can get the idea of how complex it is compared to the usual CI/CD pipeline. So we were wondering, because running the pipeline is one thing, but running it on day-to-day basis with all the things that are around might be big challenge for the tool. So we identified some key areas where we want to do some experiments to basically understand if Tekton will make it with our pipelines. So these are the areas that we identified and then we wanted to cover in our spikes or experiments. And this is a spoiler because the colors shows how it went. So the green ones went fine. We solved what we wanted, and the orange ones worked as well, but with some compromises and with some workarounds. The red ones, it's not a blocker, but it needs some more understanding and testing. So if I go from the top, the time-based execution, it's not typical for CI/CD pipelines to be triggered by a cron job. There is some bit complex way how to do that, but it's possible with the Tekton tools. You can define some event listener, and there are some mechanism of triggers where you can transform the parameters and send it to the pipeline. So we, in the end, run the pipelines with curl command in a cron job. And it sends just events to the event listener and the pipeline triggers. So that works. We were wondering how the log observability in the tool will be, because the amount of tasks is huge, and if you want to quickly navigate to some task that is causing some issues, it might not be easy. It was surprisingly easy. The Tekton has excellent CLI. It's really easy to use, and the output is sometimes more comprehensive than the UI. And the UI is well integrated into the OpenShift console. So you have everything at hand, and the user experience is really well. It's quite easy to navigate even the complex pipelines and the structure inside. The third thing that we investigated was performance. We found out that the performance is really comparable with the Argo workflows that we are using now, and there were not any significant differences. So this is also something that we don't have to worry about. Before I jump to the orange section, I would like to share how we structure our tasks, because it's important for some of the workarounds that we had to do to bypass the limitations of that we hit. And I need to stress out that the limitations that we found are not like Tekton fault or something, but it's just that we are not using Tekton for what it is intended. So we are a bit stretching the features of the Tekton in direction that was not intended. So this is our best practices for the tasks. This is basically developed over the time that we run the pipelines, and this proved to be like useful set of rules when you're designing tasks. So from the top, the task, and that's really important, the task needs to be idempotent. That means that when you run the task multiple times on the same data, you need to end up with the same results in the data lake or in the databases in the end. That's important because often you need to rerun the pipeline. For example, you were missing some data, something changed, and you need to rerun the whole processing, and you don't want your data to be screwed by this operation. So this is really important part for the sustainability of the pipelines. Next one is ability to run for past days. We need to deal with the historical data because we do some time analysis of the data. So we need to have the tasks to understand the date for which they are run. This is also important, especially for backfills of the data or when there are outages and we need to add the missing data to the history. This is also a key feature. Single responsibility, This is very useful. In our case, it means that one task equals to one table in the data lake. It's not good practice to do more things in a task, because then it gets more complex when you want to handle your tasks like in general way. For example, when you want to generate the pipelines, the task needs to be as uniform as possible. For the same reason, no data sharing between tasks. That means that the task can only take data from external source or the data lake and store the data to the data lake. No exceptions allowed to store the data to some temporary storage that's mounted to the pod and remounted somewhere else. These hacks will screw your pipelines very easily. The last two practices are well, from programmer's perspective, it's probably not the great practice, but from the maintenance of the task or the pipeline code, it proved to be practical, and it's about organization of the code. We have our task defined in Python, and one task is one class, and it includes all the metadata that are needed for building documentation, for building the pipeline definitions, and basically for navigating in the tests, let's say. So the logic is bundled together with the metadata. It's in one file. If you need to change something, you have the exact place where to look. It's also easy then to do some reviews on the merge requests, because you can easily see that there is nothing left. Because before, when we had the thing split, it happened that, for example, the documentation went outdated, and or metadata were not matching. So this worked for us. Yeah, and obvious, the execute method of the task class needs to be unified so that you can operate with the tasks generally. If this is satisfied, you can easily work with the list of tasks and use them for multiple purposes. So, for example, building the documentation, building the graphs for the pipelines, and so on. So if all the tasks are uniform, it's easy. So now let's jump to the orange part. Where are the challenges? So first one was loop support. In Argo templates, which we are using now, we are using the loops quite heavily. You can imagine a set of tasks that you need to run multiple times with different parameters. That's for what the loops are, and there is no such thing in the Tecton. This is often used when we parallelize some processing of the big data sets. We split them into small parts and run them in parallel. Also, it's used in backfills, where we tend to loop over the dates and run the whole pipelines for every day. So this is like essential feature, and it was the most challenging part of the experiments, because it forced us to change the strategy how we build the pipelines. So the solution that we found was that we now we created our own model for the pipeline, and we built the pipeline in the model, and then we have some, let's say, compiler that can transform the Python definition of the pipeline into the YAML that's understood by the Tecton. During the transformation, we basically expand the loop and render all the iterations explicitly in the YAML. The downside of this solution is that we can't have dynamic iterations. We need to set the amount of iterations before the pipeline is run. That can be limitations for some use cases. In our pipelines, this pattern could be avoided, so it's not blocker for us. But this is the probably biggest limitation of the Tekton that we found. There is something called metrics, that is new feature in alpha stage in Tekton that somehow could fix the problem, but it's not in production and it's not in OpenShift pipelines yet. So the next one, backfills. This is the most complex era, because if you imagine the backfill as a huge pipeline, when you have a pipeline run for every day, you can easily get to a huge pipeline that has thousands of tasks. This is real challenge for the environment that you run in, because it's really demanding on resources, and also it's a challenge for the tool because you stretch it to the limits. So the limitations of Tekton that we hit in this area was loop support. We already discussed that. There is no pipeline nesting. That means that the pipeline could be composed of other pipelines. That's difficult for defining the pipelines, but we overcome this with our Python model, where we allow this, and then we have some transformation code that again expands the pipeline into the expanded view, where everything is explicitly set. So the transformation of the natural model will do the work for the Tekton. Another limitation is default time limit in Tekton. Basically, Tekton tends to, by default, kill every pipeline after 1 hour of running. That's not very practical for the backfills, because they often run like several hours. And we found out that this limit can be override only when the pipeline is triggered from the command line. So that basically ruled out possibility to run the backfills from the UI. We usually run the backfills from the CLI anyway, so again, no blocker, but it's something to be aware of. What was problem is control over garbage collection of the finished pods. In the OpenShift namespaces, there is a quota on how many pods you could consume, and it includes also the finished pods that are no longer running. And you easily exceed these quotas with the backfills, because we are talking about thousands of pods that needs to be created. So and also we need, because Tekton has some kind of garbage collection, but you need to have cluster level permissions, which we don't, and it doesn't have the granularity that we need. We usually have tasks that finish successfully removed in short time, and tasks that fails, we keep them for 24 hours, basically, so they can be reviewed and altered by the person who has the watch duty over the pipeline. So we ended up with our own solution. We created simple script that does the finished task cleanup, and we run it in cron job like every hour or something, so that it removes the unwanted task from the space and frees the resources. Okay, retries. That's the only red one. We didn't find out any workaround for that. Retries are useful when you are processing data from external sources, and when there are some, I don't know, outages in the sources, for example, restarts of services and so on, you don't want to kill all your pipelines because of this. So it's useful when you have on the task defined some retry interval with some delay, and you try again for 3 times or so, and if it fails for the 3 times, the whole pipeline fails. Tekton doesn't allow us to set the delay. It is important because you need to give some time prior you retry, because you need something to change in the environment that you depend on. So this is basically we need more testing to see if it affects how we operate the pipelines on a daily basis. Setting limits on memory and cores. This is also important because some of our tasks have more than 20 gigabytes of memory required for processing of the data. So we need to carefully define the limits for every task so that they can fit in the environment. We have in total like 64 gigabytes of memory, so it's difficult to squeeze in everything. So this is important feature for us. Tekton supports that. The only issue is that the limits cannot be passed as a parameter to the task. So you can't have like generic tasks that you reuse in multiple places where you would want to change the memory limits, for example. This was solved again by our model, and we define every task in the pipeline specific, and we have no reusable tasks. So we would have to ditch this pattern in the pipeline. And the last one is day-to-day pipeline handling. We were wondering how the person that cares about the pipelines would have difficult life when they will want to watch all that's happening. So the limitations that we found were these. The long-running pipelines from UI, we already discussed that. Garbage collection also was touched. It's not possible to pause pipeline execution. Sometimes it's important to pause some pipeline that's resources hungry to leave some room for the other one that's more important to finish in time. So this is not possible, and it was resolved by a simple script that basically, if you stop the task, it will stay for a while in the Tekton. So we have script that basically produce new pipeline that contains only the tasks that were not run in the previous run. So that would be work around this way. It's a bit creepy, but sort of works. Smart retries of failed pipeline, that's similar thing. If pipeline fails somewhere in the middle, you fix the problem and you want to rerun it again. It's not possible with Tekton. You need to run the whole pipeline, which is wasting of resources. So again, we use the same script to create a new pipeline that contains only the stuff that didn't run in the previous run. So we found solution for these problems, and it seems that it could be working. What I wanted to stress out that we were quite surprised by the user experience of Tekton with these huge pipelines. It's easy to navigate in the UI, it's easy to realize what's running, what's failing, in which state the pipelines are, and it's easy to navigate in the running tasks that have plenty of tasks, and to find what you need. So that's basically it about our experiments, and now we are at the stage where we need to evaluate our findings and decide if we want to switch to the Tekton or not. So if we decide to switch, the next step will be only to create some hopefully open source project where we bundle all the workarounds and hacks in one place, and we would like this project to serve as a boilerplate for anybody who wants to create copy of our environment within, let's say, 1 day, to be able to easy start. So we want to put the scripts or the workarounds in there, along with the documentation and some follow guides how to set everything up. So that's our plan. That's it for my talk. Thank you, and now it's some time for your questions. We have, I guess, a couple of minutes. Okay.
I'm curious if you've given this feedback to them, because the software seems to be useful, but all the limitations you mentioned are things that I would actually expect the manager to have.
Yeah. Did everybody heard the question? The question was if we gave the feedback to the Tecton community. So we didn't do it yet, though most of the limitations that we found are already known and discussed in the Tecton community, in the forums. There are some solutions or discussions in progress, so we didn't find anything like extra new that would need this attention. Okay.
Or maybe more ambitious, have you considered contributing to Tecton or to others maybe some of those limitations that you used to?
Yeah, that might be an option. If we decide to go with Tecton, we might join the community and try to affect what features have priority and
You
so on.
may want to repeat the question next.
Okay. So did everybody hear that?
It's for the stream, you know.
Okay.
So
So the question is if we were considering joining the Tecton community. Sorry for that. Okay.
I think we took the similar journey as you do right now a couple years ago when we took one of our service, like traditional service, and moved it into Tecton. And one thing that became a challenge was how to properly test the task, pipeline, integrity, and so on. So have you done any research in this area as well?
Yeah, so the question was how we do testing of the pipelines and the tasks. So we have the tasks, they are defined in Python, so it's easy to do testing for that, and we have them quite well covered. Some are even like test during the auth, so the coverage is good. The problem is with the whole pipeline. There we trust to the Tecton that it's able to process the prescription as is defined, and will probably add tests for the transformation of the model of the pipeline to the Tecton code. So that's probably the area where some issues can happen. So we'll have to cover that with this test. Okay, so I think that's it because we are out of time. Thank you for your attention and see you next time.
Thank you.
start recording.
Excuse me, everybody. We're about to begin. So, welcome to a talk about exploratory data analysis techniques, and I'll give the word to our speaker.
Hello everyone, I am Akshay Gorke. I am software engineer at Red Hat, working for Red Hat Insights. And here is my first talk in the DevConf. So this is the first time I am presenting in front of such huge people. So yeah, I am starting with whatever I have and try to explain as much as easily to you that can adopt. So this is about the exploratory data analysis. Those are techniques that we follow usually in the data analysis part. So there are lots of things like today's world, it's a AI and machine learning thing. Everything is, everyone is just wanted to have an magic. Like nowadays, generative language models like ChatGPTs and the Bard and all. Like they are just huge popular. So, but everything is started with the data collection, and then processing, and then training to the models and all the things. This is the journey, whole journey, and I'm just explaining the one part of that journey related to data, because if you want the output, it should need a data. That is the input for our the journey. So in that we will explain how we can process that data, how we easily the data should be managed and processed to the model so that they can adopt it and quickly perform the operations they wanted to do. So yeah, moving ahead with that, here is the agenda for today's session. So we will first introduce about the EDA, then what differs EDA and data analysis. And there are the techniques that the data cleaning, the visualization, there are some libraries. So I'm mostly speaking up with the correlated with the Python language. That is the most popular language in data science as well. And then decision making and business strategies on that, and then we'll open for the Q&A sessions. So yeah, moving ahead with that. Is there any questions? So please ask in time. So this is the simple one, the path, the raw data, between exploratory data analysis and the output. So it is the exploratory data analysis. Before that, we will understand the raw data. Raw data is multiple types. The text, images, anything like that. In the text, we can, like suppose we're looking into the large models, language models, using the data in form of reading, understanding the knowledge books, journals, articles, and all this. So raw data is in multiple types of form. We can collect mostly we try to gather in the CSV files, the text files, and then from that collect the whatever the needed data. In a clean way. Whenever the data is generated, it's not in that clean way that models can adopt it. So that the raw data, the collection of the process, I think nowadays the huge data is generating, because we are all using internet, and for every click thousands of lines of data is generating, and it's the data. There is no limitations for data in today's world. But looking into past 2 years, like maybe 15-20 years back, so collecting the data is a big challenge that time, but not today. So now we have huge data. But now going ahead with the data analysis. So the data is in unstructured way, because we need to data in a perfect format so that we can get some understand patterns from it, get the analysis, we can improve our decision making system, try to do that. So that needs a data analysis thing. And in the exploratory data analysis, it's a somehow critical process that basically performing the initial investigation of the data, that discover patterns, anomalies, then hypotheses, and to check the assumptions as well. It is, the first good. It is a good practice to understand the data first, and then gather the insights from it as much as possible. It is the approach to extract information from unfolded data to summarize the main characteristics of the data. Because in the many times it happens that most of the people underestimate the importance of data preparation and the data exploration. It is the important step because if we have a well-defined structured data, the projects that are using the data to manage, to train their models, it will be easy, and with the very minimal time, the output will be there. So, and as we know, the output will be in the case of exploratory data analysis, the output is the data analysis. We will extract the patterns in different way. We will provide a clean data and the enriched data. That means it's all cleaned and statistically input. So I have the next slide here. Is like, because it's EDA and the data analysis. So how it can differ. Exploratory data analysis and data analysis, kind of confusing thing to everyone, but I think this table will help. So basically the future is the goal of the data analysis is answer questions, make predictions, gain better understanding on that it. But in EDA, it's just to gain insights from the meaning of the data and the data, collect such information pattern from the data. Nothing about the model training and all. Nothing about much more about the machine learning, all the things. The future time is the EDA is early in the data science process, as I said, the initial process in that, and after that the data analysis. So we can say that EDA is a part of data analysis. The data analysis is a huge big tree, and it is one part of the EDA, is one part of that. Looking into the formality feature, so EDA is less formal and data analysis is more formal, because as I said, data analysis is a big part, and the EDA is small part of that. The methods are the same. All the methods using in the EDA as already in the data analysis, but in EDA specifically I mentioned that the visualization. The visualization is basically too much focus in this, because many times it happens that there is no need of going ahead with the machine learning things to do some stuffs. We can get it from just analyzing the data itself there, and the visualization will solve our problems. So visualization is most important, because there are going ahead we will explain about what are the types of the visualization as well. But this is the important step, and as a human tendency, everyone knows that our mind captures the visualization first. Anything later than just reading or hearing or something like that. But this is the important, and this solves here most of the part. And then in the data analysis part, it's the statistics, modeling, machine learning, then all the stuff, so model training, testing, and then gathering, then again providing the output to test our data on that and getting output. And then still, if it is gathered, we need to put efforts to get getting calculating its accuracy and all the things, how much it is accurately performed there. So this is the all thing differentiates both the data analysis and EDA. Is there any question till now? Yeah. So going ahead. So first we'll explain the data cleaning techniques. So there are several techniques, but today I'm just wanting to highlight few of the techniques that are missed many times, but that are quite important in that stage. So the first one is the handling missing data. So I'll just give an example, like we have a bunch of data in this collected in the spreadsheet file, CSV file, and some in content that suppose there is some data is missing in the particular column and row, but when we analyze that, it will about us to getting a expected accuracy in that area. So how we can handle this? So we can first do that. The first step is to identify the missing values. So those will be identified in Python. There is a functions like is null or is na to identify the missing values in the data. So in that way, if we process about like we are using the pandas library in the library Python library, and it is a popular library used in the EDA technology as well. And we'll just create the data frame there, and data frame we run against. We'll check that is there any missing values in the particular column and row using these functions. Then there is next stage, like we found the missing data in that. So we can either delete the particular row, or we can either fill the value in that. So that anyway, if suppose we wanted to delete, so the simplest method, we can use the drop any functions, and it will simply delete all the rows and columns contains the missing data. So it's that simple in Python. And the next one is the imputation. This involves the replacing the missing data. Like as I said, if there is a few columns and the rows having the missing data, so we can we can fill that data with mean, sometimes median, standard deviation, and anything like that. But it's all about the data we are working with. So these things we can do as well. And then modeling as well helps us to handle the missing data. Creating the there will be models that helps to handle the missing data very well. So no need to go into that much raw things. The next thing is deleting the outliners. So first, the step in that part is to identify the outliners. To identify the outliners, it is very much important thing, because we have a data of age. Suppose we are wanted to process data in some age group of suppose 10 to 20 about the peoples we are analyzing data in that, and suppose there is a data of age of 60 and 70. So these are the outliners, because when we are processing on only those part, but there are some data that are not correlated with the what are our expectations. So that is also important to gather, because when we are trying to get a mean of that data, suppose we have a problem needs to perform operations on 10 to 20 age group people, and we just suppose get a mean of that, so it's in close to that. But if any number is 60 or 70 in that age group, that will break that accuracy in very short time in that way. So identify outliers. The methods like Z-score and visualize data using the box plots or scatter plots. The scatter plot is very much popular in that way. So we just see that these data are outlined outside that our predicted curve. Sorry. Then evaluating those outliners. So once we have identified the outliners, to evaluation determined with the valid data points. So sometimes there may be error while generating the data, while collecting the data as well. We can check in that way, or the same. Either we remove that, or we'll just figure out that why the data is wrong in that case. So that was also one thing. The same mention the inputting outliner as well. It will remove from the data set or leave a gap in the data, so can be filled with the missing value. And one more thing we can deal with outliner is the transforming the data. So we can either fully transform that the data with the whatever the average or the correlated data we are expecting in that situation. So that's what about the dealing the outliners. Moving ahead, we have few more techniques on the data cleaning. The next one is the data standardization and normalization. So the standardization in that is this technique to normalize the data in the standard format, like we use mostly in the standard deviation in that, like or mean, median, like those things. Because we need a data in a particular range in that situation. So in that, the standardization, data standardization is very much important. Like there is a data of either true or false data will be there. So it should be in a standard format. It's either true or false, not more than that. I mean nothing else from that. So we can check that, and with the help of some of the tools like scikit-learn provides standard scaler can simplify this process. So scikit-learn is also very much popular in the machine learning library, and it helps to data cleaning, data pre-processing part. That the standardization will do. The next one is the normalization. So this is also a technique that will work like a min max approach in a specific range. Like suppose there is a data of a huge number starting from 0 to millions of numbers there, but it's not possible to work on few of the numbers that are out of our range we can read. So we, in that case, we just normalize in the scale of 0 to 1, or either we can, it's up to us in which where we want to normalize in the specific range. In that way, the data will be easily readable, and it's human readable, and easy to, because there is, it will not change anything in the processing of the model. It just, we are changing the range of the data. And there is a min max scaler tools in the scikit-learn that that helps to normalize the data. In mathematically we'll say that if there is a data of large scale, like we'll go that a point, suppose there is a decimal points number as well, and fractions number, but it's quite, I mean it's hard to work with those numbers to normalize it with the scale. So basically 0 to 1 scale is very much popular in the data analysis thing, and because it's mathematically there is also few theorems that can show that 0 to 1 normalization is basically very much helpful and quite good to process with whatever our data analysis thing going on. So that's the thing about the data standardization and normalization. The next one is the handling duplicate data. So we, as far as we see the handling the missing data, the handling outliners, and the data standardization normalization. But there is one more thing, the handling duplicate data as well. So while collection data, multiple entries will be duplicated. If we have few checks there while collection, it's okay, but the data should be, I mean, the duplicate data will not be that much helpful to improve the accuracy and get the output from that. So how we can handle that? So it's so these are all the steps we need to perform while cleaning the data. And while handling the duplicate data, we'll check that all the duplicate records with the function duplicated against the pandas data frame. So all the duplicated data will be identified there, and we can just, I think it's a standardized process to remove that duplicate data. There is nothing we can do with that, like doing standardization or normalization with that, because it's a duplicate data. We need to remove that to get things done. And the removing of the duplicate data is also simple with the drop duplicates function in the function of the pandas library. Against we can run against the data frame. So it is that simple to remove that all the variables. So this is I'm specifically talking about the Python thing. There are lots of other tools we can manage. We can do those things. There are too many softwares as well that help to data cleaning. The models are creating. The models are helping in that way. But going with the basic, if we understand how it's working in the scratch, so the next things will be definitely good to understand all the things. So this is the four techniques. I think that is much more the basic one, but it is important to in the data cleaning process. There are few more data cleaning techniques like these are the data maintaining data integrity, encoding categorical variables, data integration, then cleaning. Also, documenting the data cleaning steps is also one more important thing. I would say that what we are doing is also every time in general way we are trying to document what we are doing. So the whoever the next will come there try to adopt those things very quickly, and so that's the important step when we perform the steps on a data set. So to document it, it's a good one, a good step, and the iterate the data cleaning. Like in the various these steps, we need to iterate multiple times as well. It need not be sure that we will get data in that clean way. So we need to perform various types of techniques on that with all the understanding. So moving ahead, I would like to show the data visualization techniques, and I also express the few of that will be important in that step and very easy to understand as well. The first one I already told about the scatter plots, and the scatter plots is mainly used for detecting the outlier. So there is these are the outliners, the points. So the graph shows about the cost and the weights. So whenever we're talking about this is looks like much more centric, and if we draw a line from here, it much more be linear and it's adjacent to that. So there is not looks like it is not outliners or anything that. So we can easily understand that the data will be good to go, and linear models we can use in such type of data to get the output from that linear. Suppose we are using the regression techniques, then linear regression. Which regression technique we want to use it will be helpful. So it is the widely used to relationship between continuous variable. The two variables continuously, it's linearly data we can collect. If there is any variable is here, so it is outliner, and we need to perform the data cleaning techniques, the outliner techniques over that. The next one is the bar charts. So I know everyone is used the bar charts. Many times in the Excel sheets or spreadsheet we are using bar charts to just do the thing. So I just created a children data here that represent the children and their preschool, primary school, secondary school. Those are the color that how much the school children will be using that and all the in that category. So it will this is too much simple to no need to explain much more on that. So that's the magic of visualization. I don't need to explain much of this. Going ahead with the histogram. So it's a graphical representation. It's a distribution of continuous variables. So there is a data bin. Data is distributed in the bins and display the frequency or count of values falling within the each bins, and this helps to actually shape central tendency spread the data and useful for identifying the data skewness and as well as the identifiers as well. So histogram is also most popular one in the visualization technique, and it's very much helpful in that. Going ahead, I'm also explaining few of the data techniques here. There are lots of visualization technique nowadays. I mean, if you are using tools like Tableau and Power BI and all these things, so it's very easy to do that. But we need to know about which techniques we have and how for which data which one suits well. So the line plots. The first one is the line plots, and it helps to visualize the trends over the time and the continuous sequence. So this is about the time sensitive data we can plot using the line plot. The next one is the box plot. The box plot data. So I will not put the data here. So we'll just explain. So it will provide the summary of the distribution of the data, and it displays the minimum first. It displays the minimum first quantile, mean, median, like the third quantile, the maximum values, minimum values, if there is any outliers, like that. So these box plots will help to spread skewness, central tendency, and present the outliners of the data. Then the heat maps. So the knows that heat maps also popular. Like for example, I am giving the weather data. We can visualize using the heat map with the different colors, with different color shades on that. So this is the color coding visualization. Heat map is a color coding visualization with the intensity and the magnitude of variable across the multiple categories and the dimensions. So heat map effective for showing correlations, patterns, and clustering the large data set. They are commonly used for analyzing data metrics for multivariate data. So there is the types of data: multivariate, univariate, bivariate. So univariate is simple data, and multivariate contains the multiple types of data. So these types of data will be easily visualized using the heat maps. Going ahead with the pie charts. So pie charts also. Pie charts, everyone also knows about the pie charts. The proportion or the percentage of the different categories within the data set. We can show with that. It will visualize the composition, the whole relative sizes of the different categories will be visualized using the pie charts on that. And but it is only numbering. It is limited with only numbering on that. Then geographical maps, as its name said, geographical data we can visualize. It will show the distributions across the regions, locations. I mean, in city-wise, country-wise, we will able to show the pattern from that, specific to any particular data we are working with that, like a population, like any other things we can highlight with the geographical maps. Then there is the interactive visualizations. So, like as I said, the tools like Power BI, Tableau, there is a library, Plotly, Matplotlib. Matplotlib is a simple one, but the Plotly is providing the interactive visualization, so that the next level of all these techniques will give the much more detailed data representation from the data provided in that area. So all these data analysis techniques facilitate the better understanding of the data set, and the visualization is the most important thing. As I said, it solves many problems in that area. Going ahead with the libraries mostly used in the EDA. So pandas is the first and foremost, the most popular one. The data from the multiple sources we collect the data in pandas, and pandas store it as a data frame, and it is easy to process with the rich function set of the pandas library that will help to process the data, like cleaning thing will do with that, and much more thing with this, because it has a data frames and series, and this is used mainly in the pre-processing part and the initial data investigation in the EDA process. The NumPy is a mathematical computation related library in the Python. It provides the data structure, mathematical functions and operations on the we can perform it with the arrays, matrices and the pandas data frames in the way. Matplotlib is the visualization library in Python. It's a popular one of the most popular one, and it has a variety of basic plots like line plots, scatter plots, bar plots, histogram, and many more. So visualizing data distribution relationship and pattern during EDA, it will be easy with the Matplotlib library. There is a Seaborn one. This is the high level data visualization library. Yeah, so those are the library. Then Plotly is also the interactive one, and the scikit-learn is the machine learning, and the library will help to pre-process the data as well. These are the few decision making and business strategy to identify the data driven opportunities, validate. Those are the things. So we have time, so we'll just go on a Q&A session. So I'll just read those, the decision making and business strategy we can gather from the EDA. It's validate assumptions, then mitigate risk, optimize resource allocations, then improve customer understanding, enhance product development, optimize operation and process, and monitor key performance. So we can have all these things collectively from all the EDA process. So yeah, going ahead with the Q&A session. Any question anyone has?
Any questions? Anyone? No questions?
No questions online as well.
Yeah. Okay. Thank you so much.
terrifying. Last time I did that, I snapped my wrists.
No, no, it's terrifying.
So yeah. So should I give you an opening, or will you do it one yourself?
I can do one myself.
Okay.
Yeah, thanks. Appreciate that. Well, we're all here now, I'd say. I'm David Duncan. I'm a Partner Solutions Architecture Manager, which means I'm on an alliance team, and I spend a lot of time working on Red Hat solutions.
Just move a bit to the right.
Sure. How are we? This is about right here?
Yeah.
Yeah, that's the sweet spot.
Sorry. David Duncan, Partner Solutions Architect. I work as a manager now, I guess, and I've been working on Red Hat solutions on top of AWS for the last 8 years. And before that, I worked at Red Hat as a software development engineer with Verizon. I wanted to talk a little bit about machine learning ops. Not because I want to spend a whole lot of time teaching you about ops, because I think that there's a fair amount of understanding of machine learning and, operations at Red Hat, right? I think almost every engineer here is participating in an operations space. They're doing testing, they're doing build and test methodologies almost every day. And I think that there are some very important key understandings that we have in design that are important for success. Like I said, I am an architect, and that's going to become painfully clear in the discussion points here. And I kind of put that up on the slides here to identify where it is that you're going to see me, where you're going to see my talk, and where you're going to see the things that are associated here is that I put a lot of time and effort into determining where there are target requirements, and then trying to figure out how we're going to build product technology to match those. But I do that in the context of the cloud, and I think that the cloud is a very important part of machine learning. I think we've all been inundated with conversations around generative AI, or at least I have, and I think my team's been like sick of hearing the words generative AI twice in one day, right? So, and I wanted to talk a lot more about designing for success and what key components are there and how to kind of isolate what needs to be done, and maybe this will help you as engineers or data scientists or data or machine learning engineers or practitioners to find a way to structure your ops and structure the configuration, and then look at some of the tools that are available to you. And I'm gonna, I'll get into this in a little bit, but my experience has been one in which that design has led to productization, and so I'm going to spend a lot of time talking about where those products landed and a little bit about how that development, like the development cycles and what made that go. But at Amazon, there's a practice we call well architected. And I was part of the team that designed this as well. But it's a big team, and this doesn't look very, clearly this is not a one-person job, right? So in the early days, we were just trying to figure out how we would do 5 pillars, we had 4 pillars when we started. We got 5, now there are 6, super exciting, continues to grow. But I'm constantly looking at where things focus in terms of operational excellence, in terms of cost, in terms of sustainability, how all of that effort comes together and where it goes through. And what we do at Amazon that I really like, and I'm going to get to some of the things that I really like about the design principles at Red Hat too. So, and in that open source community, especially around open infrastructure, which we have some people who represent here in the front. But there is what we call the lens, and the lens is a way of actually taking the challenges that you face in any one particular component of your infrastructure development or your line of business, and really focusing down on the core decision practices that make that happen. On the Red Hat side, what I really enjoy and what I've talked about a lot with other people who are involved in this, some of them who were on stage this morning for the keynote, like Steph and Radek, are things like architectural decision records and creating that infrastructure as code or the decision as code with a certain amount of historicity as an important component of what it is that you do in your operations. If you don't have that, then you're doomed to repeat those same decisions, right? And that is a very complex and complicated problem. So, sorry, I thought I had a little bit of a pathway, but so wherever you land in the industry, like if you're in gaming, if you're doing large-scale databases, point of sale, wherever you're collecting information from, pulling information from, doing whatever it is that you want to do, whether that's like some sort of really basic recommendation engine, or you need to do some sort of highly structured publicist group style investigation of unstructured data that may take you in whatever direction. There are lots of places to start. I personally started on the very far side of there in the HPC lens, and the HPC lens was a place where we created a structure for things that was very siloed, right? So you have a front-end node. That front-end node would communicate simple chunks of data out to a large-scale group of nodes that were there to just crunch that data and return it to the front-end node. And we don't do that in machine learning, right? Machine learning is typically done in the same way that we do Hadoop, or in a way that is opportunistic now. And the opportunistic modes are some of the things that I think are really interesting, and what it is that makes this happen. What makes me excited about this and want to talk about it outside of my team. So as you build that structure, as you build that pathway, each one of these ends up having a lens, right? You end up having a way to do this. In Red Hat, you have there's a solutions collection, and each one of those solutions collections is pretty easy to sort of review, and there are people here doing that research, and people who are actually doing research in university who are contributing to those in an open source way that I highly recommend that you spend some time reading, right, and taking some efforts there. And then also there's open infrastructure that you can participate in today to experiment and learn and build out structure and practice that's similar to what we were talking about, or what was being spoken about this morning in the keynote, which is that open source software as a service. And machine learning itself has a lot of component parts that need to be extremely well documented, well understood. And part of that is tools, part of that is finding out what it is that we're doing in our documentation. And then some of it is just basically the paperwork, right, to get things done. But ultimately, it comes together in an operations model. This is sort of the crux of what I think is really important for us, is that we have to figure out a way to ensure that we have a data processing model, and then we need to ensure that we have a way to build a continuous cycle of this. I guess I could have done this in a circle, but I didn't. I mean, and really the focus that we have is kind of starts for machine learning ops, kind of starts at collect data. These other two components are a really nice thing to have, but they don't necessarily fall straight into the operational models. They usually this is what you get handed as an engineer and want to continue forward with. So I stuck with I started leaving that out. Like, we're not going to talk about business. I can't do it. So, but I can talk about what I think is the continuous cycle here, right? So, I guess I did make a circle, and I put it on this slide, not the one before it. Each one of these steps that goes into this process has to be clearly defined, and this is something that I think is really important. Is that we find the parts of this structure in each one of the phases of the business, so that you can clearly define them. So I put in here that we were talking about this all the way to the edge. I kind of thought about it backwards, which was all the way from visualization, and all the way to the edge meant trying to find ways to tune back into whatever it is that you're evaluating, right? Whether that's the hum of a giant tank of oil or the position of a series of ships. It doesn't really matter. Each one of these component parts is really important. Anomaly detection was one of the things that I first worked on, and I think is a really important part of that edge computing process. Like, how do I get this data over here? Which data do I transfer? How important is it? What is the clear path for doing that? So, thinking about things from this perspective and listening to customers talk to me about this, I spent a lot of time trying to determine what the first component of this was going to be. A lot of that just came from like determining that models. Most people were just looking for a model, right? Like they weren't thinking to themselves, oh, I'm going to go make a model, right? They were like, I got one, and I want to really implement this. And so, if you don't know what it does, and you just need to have something that that works, you got to figure that out in this process. And this is messy, right? So this is not exactly where you want to have. This is not where you're doing ops. This is where you're trying to figure out whether or not you have a structure, and this is essentially the first part of your machine learning experience, and not where you're thinking about how you're going to properly tune this configuration. Good news, once you've done this a couple of times, you'll start to have an operational phase, and this part will look a lot like that little black dot in the middle, and you'll have an understanding of how it is that you're going to create all of these essential silos in which you can now start to create your infrastructure model, and then your CI/CD pipelines, and how that configuration comes together is really important. And then this first phase, the pilot phase, becomes a lot less messy. So for each one of the next iterations that you have, now you have this machine learning ops kind of model. And this is where you've already got the decision records. You already have all these things in place, and you can start to push them into play. And this is the great part about this conversation that we're having here, is that when you look at how much of this effort actually goes into production. And these are kind of old numbers, but they're still consistent, right? Like, I did a little background checking, and yeah, these are still good. You're still not making a whole lot of you're making big decisions. You're doing a lot of transitioning from one model to the next to try and determine exactly what it is that you're gonna get out of it. I have lots of fun stories about making those decisions, making changes in the model, retraining that model, and then determining whether or not that the aspects of that determinations were in fact valid. And explainability is like one of those things that is it's like guaranteed that you will have a lot of trouble in this space if you do not have already a process and pipeline that makes it work. So I started, I started off by, like I said, thinking about this in the context of this, and I'm highly opinionated. So I'm just going to tell you right now, like take this with a grain of salt. I am truly biased when it comes to what these operations look like in real life, like how they in fact get structured. Because I started from the simple fact that I work on a team where the center of my universe is actually OpenShift, right? So I live in a place like this. To me, represents 7 years of my life, like making this a product and turning OpenShift into a service on AWS started off by creating incremental changes that people could use in the context of previous versions of OpenShift, right? This didn't appear for us until 4, but on 3, I wrote a scale-out model because the problem with the operations for building out a structure for cloud on OpenShift was that no one had thought about how the scale would work. So scaling out was super easy. You just buy another node, and that was a fun part of that experience. But then, like a very deep pocket fun kind of experience. But the goal was, I thought, was to scale in, right? Like, I'm not using it today, so how far in can I scale? And my favorite support question that I got from that, the emergency support call that you get on GitHub, was from a customer who said, I've scaled down to 1 node and I don't seem to be able to scale back up. And well, that is true. etcd is not going to let you do that anymore. And so, and I'm sorry. But good news, you have a CloudFormation template that will deploy it all over again, and you don't have to create the auto-scaling groups that are allowing you to do that scale in and scale out. We did that, so the structure of that, the design we did was to create an auto-scaling hook configuration, and the auto-scaling hook configuration would do all of the node setup, and then when you wanted to scale down, the auto-scaling hooks allowed you to tear down the node in a proper way in the old OpenShift container platform model. And so this was the start of getting those people who were making the business decisions very excited about the fact that they had an incorporated model. And so from the, as a foundational layer, that was the thing that created the excitement that made 2 business decisions, one on the Red Hat side and one on the AWS side, that brought us a service that would in fact support doing a lot of that work. Now, everywhere you go, that product design started to become a really important part of how it is that we build this concept of 2 platforms talking to each other, right? And in fact, integrated together. Being integrated together means that you have to solve other problems on top of the problems that you have for just creating a container-based platform, right? Like, we have many different selections, so now there's many different ways to deploy OpenShift on AWS now, right? This is super, suddenly you've got a big choice to make on how this is going to happen, who's going to manage it, what's going to be going on. And then you've got these other things that you can do, which are the vanilla options. What am I getting myself into? Oh my gosh, now I've got a practice that has to make all these decisions. And that's where the decision records come in. It's like, you can go back through those, you can make a single decision, and then you can make another one based on that. And in fact, there's some in the blueprints for the open infrastructure that talk about some of those like failures and the failed decisions, or the advantage of one option over another in terms of like making a decision about one open source project or platform component over another. And then relating those back to best practice, that's what that well-architected lens is for. And the components that you find in there start to force, it's a forcing function to ask questions like, is this sustainable? Does this, apply operational excellence? Am I getting scalability that I expected to get? So using those techniques and the technologies that are associated with that kind of question-answer experience is a great way to form that body. So take the those 6 phases of the operations, and then look at how you're going to put that together, and you'll start to see that there are some places, there are going to be some big holes. So you need an inventory, right? You need an operational inventory, and so once I looked in and said, we've got Roses like on the way. What else are we going to need? Well, it turns out that you need a way to build out this infrastructure that is consistent with your expectations. I chose Ansible, so an obvious choice, right? I'm in an alliances team. I know. Puts food on my table. But Ansible is also, a personal favorite. I can make the decision for that outside of my experience, right? But there are some things that I think are important, and they're supported by technology, by creating enthusiasm for that same kind of technology. So identifying that was something that was really important made me continue to talk to our CloudFormation team and say, hey, I really like what I can do with Ansible, and I don't like writing this JSON target and then not being able to iterate very well or find ways to do more minimal tests. That team decided that they didn't like having just one way to do it, and that they wanted to be able to incorporate that strategy into what they were doing. And so that's how the Cloud Control API was born, is out of that iteration, out of us talking back and forth. And that didn't just happen to Ansible. It happened because tools were changing, right? Chef was going away, Puppet's going away, nobody wants to use those anymore. The server model doesn't work for us. And it certainly doesn't work for machine learning, and I'll get more into that through this, is that we were looking for kind of an easy way to get to do the discovery for the resources, to create a way of building out those best practices in an iterative model, and also in a way that was easily consumable. So Ansible becomes kind of an easy place for us all to create opinionated decisions. On the other hand, it travels well. So it doesn't. So I don't need this is like just one aspect of it. And yes, this is David's opinionated inventory. I'm not. When you get out to the edge, you're going to use different collections. You're going to use a different experience. There's going to be a different experience, but it's all going to be part of your execution environment. And support infrastructure as code. So originally there was nothing on AWS except the Red Hat Enterprise Linux. In fact, that was the only thing that ran on Amazon originally. In 2006, you could get a Red Hat box, right? That was it. And once we started to look at what it was that we were doing with data, there were a lot of places for us to go with that, and some of the other things that became kind of obvious was, well, we still need high availability, right? High availability configurations were absolutely necessary, and we still need a way to manage data at the edge. There are lots of times where you're collecting a lot of information, and you need to put that information into a large-scale data lake. And we found that there were some options that allowed us, that Microsoft SQL allowed us to use in collecting that data at the edge, right? Like, made it very easy for us to have simple communications over VPN to collect small amounts of data, and then pass that data into buckets that were associated with longer-term storage. And that has driven a lot of variation in the way that we use workloads. So, looking at kind of an example of how we build a pipeline, we start with code. That includes the infrastructure as code, and the OpenShift kind of stays in the middle. In the early days of machine learning for data scientists and things like that, and people who were actually like crunching the actual algorithms and trying to determine whether or not they're fully functional, we have this tool that they call the deep learning AMI, and the deep learning AMI is like was exactly what I didn't want it to be. But it works. It seems to work. Everybody loves it. It was a collection of basically every scientific library that you could think of for Python, Ruby, and R that just like dumped into one machine image with all of the NVIDIA CUDA drivers and everything, and then you can just basically leverage that for component parts. But that doesn't make a pipeline, right? And so in this case, this is outside of the pilot phase. These are some kind of the things that you end up doing to get structured data. And this represents, for me, a data practitioner. So if you're looking at the way that this works, you'll see that I've got up in the farther right corner the concept of using Amazon Athena, which is a way of building out a SQL style analysis of the contents of an S3 bucket. So if you have structured data or mildly structured data, you can create a configuration and get something back. And then AWS Glue is a way to create tokens and to tag data so that it goes from an unstructured to a more structured model. And you can get those artifacts and get the trained model from that experience, and then you can push that into production. So once you've got your approval process to kind of transfer that over on the top. Once you have an approval process, you can move that over into your production cluster. That cluster can be, can come with you, and then, the artifacts can come with you. Your trained model can come with you. You can pull the batch inference production data from there, and then use that model in a way that is consistent with your business requirements, right? Your recommendation engine or whatever. So that whole process is exactly what I think of when we bring this out in experience, and that's why there are tons of tools for doing this. There's single node Outpost is an edge solution that we can use. We can use that in the context of Greengrass. You can, in fact, for the AWS experience, right? We have a small method for doing basically serverless functions at the edge, and you can collect that information and stick it into S3. And then this is the simplified way. As you become more, as your data engineer refines this more and more, you may find that the basic tools no longer work, and you'll create a more bespoke model that is consistent with building out on the ROSA experience, where the Open Data Hub tools will take you through that whole process. So that effectively is everything that I have to talk about today, and then to say that this is a great opportunity to talk about machine learning ops and what makes this work, and to see a little bit of an example of from an architecture point of view what it looks like. Does anybody have any questions?
I have one. You briefly mentioned monitoring and model drift. So in your experience, how difficult was it to set up both the monitoring part and the model drift, like dealing with it, retraining? Like how difficult was the whole cycle? for you?
Well, so for me, model drift is less of a concern because obviously I'm more focused on operations than I am on the models themselves. But what I see from my friends is that because the training is happening so consistently, when you put this into operation, like if you've got the Ansible models that are like building up the systems, and then you're doing your basic training, and then you've got that model in connection with your data. And I didn't mention public data sets, but public data sets are like a huge help in terms of training, and they come across as an S3 bucket. In fact, quite commonly I will use those in the context of OpenShift, right? So I'll just grab that and then just put the assignment for the public data set in an Open Data Hub workspace. So those, like, building out the YAML structure for that and making it work reduces the amount of effort necessary for retraining. Right, and so that's what I was talking about. Like, the pilot phase is messy, and there will be much gnashing of teeth while you try to push that back together. Which is, again, why I don't like the machine learning Omni. Even though it's incredibly reproducible because you just pick one and you just use it over and over again. But if there's a security vulnerability or something, or if there's a modification that you really want to take advantage of, then you have to switch your entire environment, right? So. Yeah. Any other question?
This session is still running. I'm sorry.
So model serving is obviously a big part of operating model. So all the inference part. A couple of years back, there was a myriad of young projects trying to solve that. Starting from just wrap it in a Flask application and then deploy it as a container. You had TF-Serve and some other projects trying to solve that. I wonder if we now are converging to a more cohesive and consistent deployment model when it comes to inference part, and maybe what is Amazon doing on their backends for all their AI services.
Yeah.
Is it always just homegrown, depending on the use case, or is there some convergence?
I think there's so there is always an opinionated convergence. So if you look at Red Hat, I'll start right there. If you look at how Red Hat does this with the Open Data Hub, right? You have all the tools that are associated there, and then you have a way to just generate, the standardized structure is to support the pilot phase in Jupyter Notebooks, and then create that configuration and maintain those models in specific containers so that you can have that container space. But at Amazon, the way to do that is they create SageMaker, then they use some very opinionated modules, and they say, you, Mr. Customer, can use all of these exactly the way that they exist today, or you can maybe later make a decision on how you're going to use it. Use a different one, interchange them. But in my opinion, part of what we did, like building RHEL Workstation on top of AWS, was to create spaces where if you knew what you wanted to do in that messy phase, you could have immediate access to the right kind of hardware from a Red Hat instance, or and you would know how to, and create an open source model so that you know how to build that on other platforms that you might want to use in your configuration. I think we're out of time.
1 more minute.
Oh, okay, 1 more minute. Another question?
So you do mention Amazon SageMaker. So I've been using Amazon SageMaker for a while. I wonder, is primarily intended for training models, but do you have any sort of other service that would accompany to the whole?
Well, okay. So talking about it from the perspective of the Amazon products, yes. So SageMaker, I think, is really meant to leverage models that are there, and then you have the ability to train, to do some additional training on some of the extant models, and then you can add your own if you want to in that process. There is what they call machine learning ops, which is basically a service for machine learning ops that is available there. For me, obviously, that's not where my work extends into how I can make this work on the Red Hat Open Data Science model, which kind of gives you a similar kind of environment, but done in a very open source way and a way that is achievable on other platforms, right? So if you have a hybrid scenario and you want to have the same experience from your on-premises to your public cloud experience, then I would say, you can do that in the context of Open Data Science or Open Data Hub, and that the SageMaker would give you sort of similar tools, right, in that sense. Like, if I wanted to go and build a cluster and then use Dask to handle a complex problem across a suite of systems, I can do that as easily in the context of an OpenShift cluster on AWS as I can building that out in terms of machine learning ops with SageMaker and the SageMaker notebooks.
Well, it was a very nice talk. And if you have any further questions, I think you'd be more than glad
I'd be
to answer
excited
them
to
after.
talk about it. Yeah,
Yeah.
talk about it all day.
I think you're on.
Hey everyone, I started with jokes already, so now it's time to get serious. Welcome, first of all. It's my first time here at the conference in Brno, but also in Czech Republic, and so far, thumbs up for everything. Thank you for making it like that. My name is Ivica, and I will try to make the next 25 to 35 minutes interesting for you. And because we are now in the post-lunch sleepy time or energy dip, I'll try to make this interesting, I promise. If you want to make it interactive, you can just, you know the drill, right? Ask your questions, we will answer all of them in the end, so there will be a slide for that. But also, we need to get our blood flowing, we need to keep this interesting, as I said. So is there anyone here in the audience that considers themselves to be a data engineer or someone that works with ETL, with data processing, with whatever? Just don't be shy. Okay, a few of you, including myself. Well, I'm lying actually, but I want to provide an example for you guys. Okay, but did you also hear that data is the new oil? Kind of? Yes? No? What about this one? Data is the new gold. I don't know, I heard it, and I'm not even a data engineer, right? But I also agree with both of those statements because they are true. And when we talk about ETL, the E in ETL stands for extracting. And it means getting something out. In our case, it means getting the gold out of the ground. And it is hard work, absolutely. I haven't tried it, but I heard dwarves talking about it. Because first of all, you need to know where the gold is. And even if you know where the gold is, you need a permit to dig. Well, there could also be dragons guarding it. You can just ask Bilbo Baggins, he knows for sure. But knowing where to dig is half of the story. Because the other half is getting the permit. And usually in my own country, you need to bribe a few people. You need to, you know, lube and grease up and whatnot. Yes, it is how it works. In any case, the scenario that we will go through today goes exactly like that. You know there is gold in those hills, and you have the permit, but the local clerk that gave you the permit was just a little bit on the bottle, and the permit says you need to dig from your home. What? Well, exactly. We are going to dig for gold from our own home. And speaking about home, my professional home is one of the largest fashion companies that you never heard of. And it's called Bestseller. But I'm hopeful that you heard for at least a few of those brands, such as Jack & Jones, or Vero Moda, or Only, or about 18 of the other ones. As I said, my name is Ivica, and I'm definitely not a dwarf, although my Dutch colleagues might disagree with that. And I work as a data platform team lead in said company, Bestseller. And what we do is we essentially provide the analytics platform to our colleagues and to the stakeholders so that they can make business decisions and also be informed about those decisions. And some of those decisions are, do I buy this shirt? Is it going to sell? How many of those do I need? When do I show them on the website? When do I take them down? And do all of that 9 months in advance, because you don't buy it today for tomorrow, you buy it for the next season. So there are challenges in running this platform and providing these insights. And one of those challenges is definitely around data governance and data residency. And the scenario that I want to share with you today is about how you can use Apache Airflow and ECS Anywhere to solve those challenges. But we first need to understand what this residency is. What does it mean? I'm not a native English speaker, you can probably hear that. So I reached out for the dictionary. There it is. Residency is a fact of living somewhere, where you reside. In my example, I'm living in the Netherlands. That's where I'm a resident. But also the fact that I'm allowed to live there is regulated by law. I also pay taxes there, which is, again, regulated by law. Which brings us to the next term, being governance. So what does it mean to govern something? a society, a country, an organization? Well, it means coming up with laws and making sure that they are enforced within this organization or a country. Now that we understand what the problem is and what residency and governance are, let's also see how the statement of Acme, the company that makes everything, acquired a competitor, can be turned into Acme acquired a competitor in the US, and now they have problems with paying Christmas bonuses. And it's not actually what you think. They still have money to pay Christmas bonuses, but they cannot do it. In the world of big fish acquires small fish, our own big fish, Acme, acquired their US competitor called Cyberdyne Systems. Nothing wrong with that, right? Companies buy companies. But if we consider that these two companies are in two different geographic regions of the world with different governing bodies and different laws around data processing, that's when things start to get interesting or nasty, depending on who you ask, right? Because we absolutely know that there is valuable data hosted somewhere in the US where Cyberdyne Systems is. And the leadership from Acme would give pretty much anything to get insights from that data. But their ETL tool of choice is hosted somewhere in the EU. That's a problem. Because you are not allowed by law to process US citizen data outside of the US. So you have to process the data in the US, and that's what the goal is. And that is the challenge that we have before us, because we need to get to that goal from our own home. Clear? We get it? Okay. Essentially, we are in this situation architectural. As I said, Acme, an existing company, has their infrastructure hosted somewhere in the EU. They have a container management platform, they also have an ETL platform, and what they recently bought is 2 data centers, one of them in New York, the other one is in San Francisco. It is, of course, technically possible to load the data that is somewhere remote, but we are not allowed to do this. This is where I would ask you to pick up your phone, scan this, and tell me how would you approach the problem? How would you solve it? I'm going to give you a few minutes and drink some foods. Okay. Okay, I was in the blue half a few months ago, yes. Okay. So pretty even distribution, I would say. Yes, thank you for making it more even. Yes. How it becomes a game, right? There's a whole concept of gamification and everything. This is how you gamify. Okay, but whatever the results are, I'm gonna anyways tell you that they're all wrong. So let's just continue. Roughly a third of you said, let's do a site-to-site VPN. Right? A valid solution. There is nothing wrong with it until you consider the complexity. Because you need skilled people to set it up and to monitor it. You need to make sure, because this is now a critical part of your infrastructure, you need to make sure there's 2 redundant links, you need to make sure there's people on call to, babysit it when it needs to be babysit. And we're talking about 2 geographic locations, so different time zones. So you need people around the clock, and you need to pay them to pick up PagerDuty phone calls. Not ideal. Okay? Another approach, as you said, could be to run the ETL tool of choice per location. It's fairly easy technically. Most of them are containerized, so you just run them in all locations. But what if you have 17 locations? What if you have 25 or 250? Who's going to manage that? Who's going to manage all the access to all of those tools? Because they are now separate tools. How do you manage permissions that these tools have to the data sets that you want them to process? How do you reconcile logs? You have dependencies between jobs in location 1 and location 17. One of them fails. How do you reconcile logs in multiple locations? It simply becomes an operational nightmare very quickly. So let's not do this. Maybe it is safer to cry in a corner. But you know who didn't cry in a corner? People that were selling shovels during a gold rush. And I don't have any shovels on me, but I would like to introduce you to two shovels, which are Apache Airflow and AWS's ECS. And let's talk about them briefly. By the way, anyone in the room using any one of these tools? Okay. Any happy users of those tools? Yes, 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 that's what I want to see, yes. Okay. AWS ECS is the Elastic Container Service, and it is essentially a container management platform. Some call it poor man's Kubernetes. Maybe it is, maybe it isn't, I don't know. But what I do know is that it allows you to run containers, to scale them, to make sure that they keep running, and it does the job right in most cases. It is far from perfect, but it works. And one of the best features of it is the integration into the entire AWS ecosystem. If you need to handle permissions for those containers, it's IAM. If you need to change firewall rules for those containers, it's VPC, again, on AWS side. The way we use ECS within Bestseller is to run services 24/7, and mainly the services that make or break our business. So things like refund services and order management systems and returns and anything essentially that, as I said, can make or break our business. But we also run scheduled jobs, we also run one-off containers once a month when we need something to be done, etc. And those processes are still important. They can be waited on, but they are still business critical. And one of the issues that ECS doesn't do is container orchestration. So it's not going to wait for something to happen to run your container. It does it on a schedule, right? So how do you orchestrate this? Well, that's where Apache Airflow comes in, because it is an open source platform for orchestrating and for developing workflows, specifically that have dependencies between them. What it does is it allows you to create workflows called DAGs, D-A-G, DAGs, through Python code, which means that you can version control it, you can collaborate it with you can collaborate on them with your teammates, and have all the good stuff that comes from Git, right? But you can also create intricate dependencies between jobs in your workflow, and you can also create dependencies between the workflows themselves. So if we look at a very simple example of making a pizza, I guess you did it at least once in your life, right? So how does it go? You prepare the toppings, you prepare the base, and then you bake it. But you can also do the toppings and the base in parallel. Your partner can do one, you do the other, the chopping, the taking care of everything that falls on the floor, etc. So you can do it in parallel, and in the end you will make a pizza, but you need both of these processes to finish first before you put them together. Well, that's exactly what Airflow does. It allows you to organize these jobs or these tasks into workflows that they call DAGs. And then you can configure dependencies between them, and you can say which comes first, which runs in parallel, etc., etc. And keep in mind, Airflow is not imposing these dependencies. They come from the real world. You cannot make pizza without the dough and the toppings. You can without, what's it called, pineapple? You can do without pineapple, right? That's all we do. The real power of Airflow is that it comes with batteries included, and these batteries have been committed by the community because it is an open source tool. There's more than 10 million installs per month, so you could say it's pretty popular. Big companies, big players such as Adobe and Adyen and Airbnb and LinkedIn, etc., they all use it because it is a good tool. But let's talk about these batteries. So one of the first batteries that comes included with Airflow is called operators. So what do they do? Operate right? Not as doctors would operate, but they just operate on something else. As you can see in this example, we are using the redshift operator. And what it allows you to do is to provide a SQL query which is going to be executed on a redshift cluster without you having to know too much about how to do that thing. That's what operators do. They do the heavy lifting for us so that we don't have to. Make sense? Okay. So enough about EC2 and Airflow. Let's talk about the features that make them work together and that make them work well together. The first one is called ECS Anywhere, and it is essentially a feature that allows you to reuse the existing infrastructure that you have, including Raspberry Pis, to extend your cluster and to run containers on those machines. The next one would be the Airflow's ECS operator, and I think you can guess pretty much what this guy does. It allows you to run containers on ECS. You already see how they work together? Yes? No? Well, I'm here to tell you. Okay, so with these two, essentially, what we can do is we can orchestrate containers on our existing infrastructure using this guy. That would be the ECS operator for Airflow. And what it does is it essentially runs a container somewhere on ECS. Looking at the final solution architecture, this is what we have. This is what we ended up with when we said, okay, let's use ECS and Airflow together. But there's a lot of going on this diagram, right? So let's go through it piece by piece. This is the existing container management platform, the existing ECS. And it is somewhere in the EU. We have it, it's up and running, it's making money, it's all good. What we also have is the existing ETL solution. Again, located somewhere in the EU. It's also running, it's providing value. But then we also have these two data centers that are remote and that are untouchable for us up to this point. One of them in New York, but we can extend the existing container management platform to use this data center as well by using ECS Anywhere. And we can do the same for the for the San Francisco office, sorry. So now that we understand what the final architecture looks like, let's see it in practice. This would be the demo time, and usually experience has taught me that doing live demos is a no-no. Demo gods are not favorable. So I will just show you screenshots of what I did. It's easier, and you have to trust me. That's why it's easy, right? Cool. If you don't trust me, everything that I'm showing here is available in a repository. It's everything as code, so you can just run this on your own and just prove me wrong, please. Okay. So the thing that we are going to do first is just show the ETL scripts that we have, because they are the basis of everything after. And we have two of them. The first one is the bonus calculation script. We want to give our people the Christmas bonus that they earned working hard for us. And the script itself is fairly simple. It just loads a CSV file, does some data processing, and then saves the result into another CSV file and uploads it into AWS S3. The second script that we have is the tax calculation, and this is the one that calculates company taxes based on the offices that they have, lease contracts, whatever. It's too much for me to go into. And it also must include these new branch offices in the US. And it is very similar to the first ETL script that we have. Load CSV data, process it, upload the results back into S3, and watch the run code. So let's verify that they work. This guy said he doesn't trust me, so I'm going to have a screenshot to prove him wrong. Okay, I can just run the script like this with the valid inputs that it has. And a few seconds later, if I list the contents of this S3 bucket, you can see I did it this morning. Sure enough, it works. The result file is there. The same goes for the bonus calculation script. It's pretty much the same deal, same steps. Same target, same distance. We get the results. Nice. And since we saw that these scripts are working on their own, standalone, now would be the time to containerize them, because remember, we need to run these scripts as containers. They need to be scheduled somehow. Docker files, Docker build, Docker push, boring. The only thing you need to know is they build and I push the container where it needs to be. Because the next step is to actually use that container in an architecture like this one. So what I have running right now is two sets of resources. The orange area are the resources running in AWS, provisioned to the same code that I mentioned. But we also have the blue area here, and no, I didn't buy any property in New York or San Francisco. I just spun up 2 VMs. They're good enough. And what I also did is I extended the existing container platform to now use these virtual machines that I have running on my machine as external cluster. Make sense? Clear? Okay. Why 2? Well, that's because we have 2 ETL scripts. One for Christmas bonus, one for tax calculation. And that's because 2 of these machines have access to a different data set. One host has access only to employee data, while the other host only has access to property data and lease contracts and similar. Which means that our infrastructure is now ready to run a container, to run this ETL script as a container and see if it works. I'm here just using AWS CLI and essentially telling it, hey, go run this thing on this cluster here, and please use the external part of the cluster itself, which is the 2 VMs that I spoke about. And sure enough, looking at the logs, it works. It does something, it doesn't complain. To me, that's good enough. But you can also notice that it runs on one of these machines. It runs on the bonus host, as I call it. So what would happen if I do the same thing again? Remember, we have 2 machines. Would it still run on the same one? Or would it use a different machine? I see a lot of people yawning, so let's do some stretching again. Who of you think, by raising your hand, that the next time I run the container is going to run on the same machine? Okay. And which of you think that it is going to run on a different machine? Okay. You probably noticed I raised both hands because, yeah, both is true. And that's thanks to the round-robin algorithm and the 50% chance of running on an incorrect machine, because we have 2 of them, right? The host itself is not wrong. This is the situation that we end up with, because the task can run on both of those. And it's a no-no, because the hosts are not wrong, it's the data set that they have access to is wrong. So the tax ETL script can run on the bonus host and say, no can do, boss, I don't have access to these files. So how do we make this work? How do we approach this?
Tags.
Sorry?
Tags.
Tags, nice one. The real metadata tags or some other type of tag?
It says tags.
Okay, well, you're not wrong, my friend. Thank you for speaking up. This here represents the algorithm, let's say, behind how ECS schedules a task, how it chooses where to run your container. And as you can see, it first looks at CPU and memory, meaning, hey, can I run this container on this much memory? And then if it can, it then looks at the location, instance type, etc., meaning that you can tell your container, hey, please run on instances that have access to a GPU if you need a GPU. Or you can tell them, hey, please run in this region of AWS because that's where my other infrastructure is. But what you can also use is something called custom attributes or custom placement constraints. And as the name suggests, they are completely custom, meaning that you can tag your container instances with whatever you wish, and then use those tags when you run your container. This is something that we can use to tell one of these ETL scripts to run here or there or nowhere, because you can screw up these tags or these attributes and the container will simply not be scheduled. This is how these custom attributes are set. What we have essentially is a custom attribute called purpose with the value of bonus, and the same goes for the other one. Purpose, tax. And as you can see, I set them on 2 different container instances, so now they are completely separate. What we can also do is, when we run the container, when we try to schedule it, we can now say, hey, please include this placement constraint and only run this container on this specific set of machines or this one machine. And of course, by using these task placement constraints and custom attributes that we just set, we can now guarantee that the proper scheduling is going to happen, such as this one. This is the last step, but also the most complicated one. And now is the time to schedule these ETL containers on our very specific infrastructure using Airflow and using everything that we mentioned up to this point. So what I did is I went ahead and I created 2 tags in Airflow. One of them for Christmas bonus, one of them for the tax calculation, and they are pretty similar in code. And I did so by using this guy that we already met like 10 minutes ago, the ECS run task operator. To schedule these containers, we can use code like this. And if you have a Kenai, you can also notice that it's very similar to how we ran the container by using the AWS CLI. That's simply because we provide the name of the cluster where we want this thing to run. We also specify which task definition or which container definition to use, where to run it, meaning external instances or internal. But we can also provide the placement constraint saying, hey dude, this is the Christmas bonus calculation ETL script. Please run it on instances whose attribute purpose equals bonus. And ECS is going to respect this. Now, the DAG, the container itself, has been scheduled. It ran, as you can see from the logs. We also can see that the exit code is 0. What does 0 mean? Can you someone remind me? Yeah? It was successful, but what the hell happened just now? Do we know? Okay, well, let's show it a bit. So the first thing that happened is that Airflow, as a tool, ran a DAG. It scheduled this DAG. And the DAG itself started a container on ECS. And then when ECS said, okay, this guy wants to schedule a container on this specific machine type, in this specific location, and I can do this. So ECS schedules a container on the remote data center, on the remote machine that we have, with access to proper data. That's when the container executes, it starts the ETL script, it chugs along, processes the file, and in the end, it uploads the results back to Europe. And this is fine, because these are just the results. It didn't upload any of the data on US citizens, it just uploaded a bunch of IDs and numbers. So this is fine, we are still compliant. And because time is running out and we are having fun, we are having fun, right? Yes, thank you. It's time to recap. We saw that ETL processes can be pretty different. They can be simple, they can be complex, they can be blue, white, ran manually, scheduled, etc. But what they are is they are necessary because the data that we process comes in many shapes and forms and it needs to be transformed and processed and cleaned, etc. You know this better than I do probably. What we also saw is that ECS is the right tool for the job, but it does come with trade-offs. We also saw that Airflow is the right tool for the job, but it needs a bit of a boost from a container technology started more than 10 years ago, proving that Docker is still valuable, right, if you use it in the right way. And in the end, something that I learned in my career along the way is that there are technical solutions to technical problems, but there are also non-technical solutions to technical problems and vice versa. And the sooner you get this, the sooner you can advance your career and become the famous 10x engineer that you can be. With this, I would very much like to thank you for your time and for listening to me. If you have any questions, you can shout them like here, but you can also use our good friend Slido and ask any questions that you may have.
Okay, so we still have some time. Please ask those questions before people start pouring in again.
If you have them. If not, just catch me around, please.
From you mentioned your task uploaded back process data. This process data just scrubbed by output of container.
No, it is a CSV file that is created by the container.
CSV file and
With-
this automatically, or it's part of job and migration from S3 to our native.
Yeah, it is a part of the ETL script. Essentially, the ETL script is completely custom. It can be whatever. This is just a stupid example of calculating Christmas bonuses. So it can be whichever you like.
Okay.
Yeah. There was another question here. Yes, please. I think you raised your hand. Maybe I'm wrong.
It was me before.
Okay, yeah, please, go ahead.
Please go ahead.
You were mentioning the placement constraints thing.
Yes.
I was thinking, so basically it's Airflow that does the schedule, but Kubernetes
Yes.
already has things and toleration. I mean, it's basically duplicating this same thing, or it's running things and tolerations under the hood.
Okay, so the question is about custom task placement constraints and Airflow scheduling this.
Yes.
And then the point is, what's bugging you?
So Kubernetes already has that solved
Okay.
by specifying which workloads are supposed to run specific node. So I
Okay.
was wondering why Airflow is duplicating that task. Because there is that specific operator, so Airflow is not meant to
Yes.
work with Kubernetes, so it's not Kubernetes native. Right?
It can work with Kubernetes as well. In this case, it was working with AWS ECS, and the reason it is duplicating the work and it's touching on the or encroaching on the infrastructure part is because it is scheduling this. Airflow is the orchestrator now. You are giving it the power to do so.
And also operators.
Yes.
Because without operators and using containerization, you should write by your own everything. And this inside Airflow,
Yeah.
just few strings and everything is done.
In this very specific example, yes, because the operator itself is simple and we are using the task. But what's the real power of this is that you can, because Airflow is written in Python and those workflows are written in Python. But if you're not someone that does Python, if you prefer Rust or whichever else, containers allow you to do it. You're not locked into Python anymore. I think we are out of time.
We still have 2 minutes.
Okay, please. Go
So-
ahead.
Have you maybe considered solutions?
2 more minutes, please. The session is still running.
About other solutions that might have done similar job,
Yes.
but with other technologies?
Yeah, so the question is, have we considered using other solutions such as Lambdas to achieve the same task? And yes, it's a very valid question, but you have to think again about if the tool has everything you need. Lambda is completely custom. It's the code that you put into it that is valuable. And Lambda also has limitations such as how much can it scale in terms of memory, but also time limitations because it can only run for 15 minutes. And what if we have a 10 gig CSV file that's going to take 3 hours to process? Also, the reason why we are using Airflow is because it is the ETL tool of choice and it comes with batteries included, meaning we don't have to write the CSV processing logic. It does it for us. Please go ahead.
Okay,
Yeah, you.
so I was just wondering about the experience of running. I guess you are running your own Airflow instance, so basically installing and managing it, upgrading it.
Both. Yes.
And what was the experience? Like, is it like maintenance, heavy maintenance free? Like, how do you?
Yeah. Depends on how you look at it. So the question is, are we running our own Airflow instance, and is it difficult to manage it, or is it difficult to just keep it running? That's why I said we have both. We have the old Airflow, which is self-managed containers, and it is not very much updated because we are bad at doing this. It's not Airflow, it's us. It's, yeah, like every relationship. Well, we also have another deployment of Airflow, which is completely managed by AWS, and that one is much easier to work with, but also costs like 5 or 6 times more per month.
No.
Yes. If there are no more questions, thank you very much again for attending.
interesting things, differences between correlation and causation. Okay, thank you very much. So yeah, let's dive into it. So what I'm working on in Red Hat is a team called Connected Custom Experience, where in a nutshell we are collecting the health data from the OpenShift clusters of our customers, if they are okay with that. We do or try to do some magic and then provide the profit in terms of better user experience for the customers. It might be, services they can use based on this data. It might be improving the product based on the analytics and so on. So we basically are focusing on the phase 2 of this strategy, and that's what I'm spending most of my time. And in detail, what I do is I see problematic clusters, and by clusters I mean OpenShift instances. Because if the OpenShift instance is happy, I don't see it, like it's boring, right? We are interested in the stuff or in the clusters that have some problems. So basically, we are looking at the problematic clusters and trying to reason about that, and the rest of this presentation will be tightly coupled with this. I'm not data scientist. I'm not data scientist by training, but I do data science by accident maybe, or by necessity, because without that you can't do much in this business. So that's I have interesting relation with the data science. It's love-hate relationship, I would say. I love doing that. Data science doesn't love me always, but we are doing well. One of the problems of the OpenShift when it comes to looking at the problems or understanding problems is the underlying Prometheus telemetry and alerting, and the distributed notion of the Kubernetes, where each component has basically their own definitions of what's the problem. And the problem is when there is some central issue, some root cause in the cluster, multiple components start complaining about that. So what you end up having is some timeline where you have multiple alerts triggering at the same time. So there are maybe 20 different alerts that we've seen around 9 a.m., but there were not 20 problems that the cluster has seen. Right? It might be 1, 2, maybe at most 3, but the problems are different than the signal that we are having. So the question is, can we do something to reason better and show closer the root cause of that, which I believe I described in this next slide. Basically, we try to group these alerts, these signals that we have about the cluster into some related things, and ideally also be able to reason about the cause and the consequence of these problems. And that's why this talk is about correlation and causation, because it's tightly coupled with this particular problem. So we now will move away a bit from the OpenShift itself, and I will talk about this problem in more broader terms. So one thing when it comes to the grouping, many times you start thinking about maybe clustering, and people that have tried or seen some machine learning thing, that's the first thing that they suggest. Of course, there's clustering algorithms, just do that. And the question is really, should I do this path, go this path, or should I not? That's the question. So we tried that. We tried some clustering algorithms, so we did our embeddings thing, we did principal component analysis, we did dimensional reduction, we did clustering algorithms of all sorts, and it kind of works. One of the problems that we had there is that once, these are basically different symptoms that, if they are close together, somehow mean that they were related or happening at the same time. The problem with this approach is it's hard to interpret this. You can kind of feel that they are probably related, but there is some limitations of reasoning about it. That's why in machine learning, often it's mentioned that there is problem with explainability. That's one of the reasons. It does something, but you really can't tell much how it does. So we can also try different approach, and that's what this talk will be about mostly. So you have all this fancy machine learning, deep learning, artificial intelligence stuff, in this tech videos, but there is still this thing called statistics that has been around for some time, and I don't think we should forget about that. So we'll be taking a bit more statistical approach on trying to find these relations. And I believe that's the end of my slides. And now I will switch to this different tab, and that's how you know that there is some data science going on, because all of a sudden there is a Jupyter notebook. Right? Like there's some big Jupyter notebooks, you can be sure that there is some data science going on. There might be some other things going on in Jupyter notebook, but we have also data, so there's something with data. And in the next cell, we also have some latex equations, so that's science, right? So we have data, we have science, so we are doing data science. Before we jump to some data, I prepared small magic trick. I never trained that, so it might not work at all. So I have here, I wrote my kids with for some toys that I have in this bag, and I have a special capability which is called chromatic ear, which means that I can hear the color. Right? So let's try. I've never tried it. I just have a feeling that I know that. I know how to do it. So I randomly choose some item and play silence. There's some voice. Okay. Okay. I think it's red. It's red. Right? I haven't looked at it. I just heard that. So so how did I do that?
You got only red objects in the bag.
Oh, I forgot to show you.
Oh, okay.
I have different colors.
Different
That's-
shades, right?
I'm doing it. No, the first time I'm doing this, so yeah, I'm doing some mistakes. Of course, there's a trick, and it's a really silly one. So
it's that the cube is the only one
yes,
that's red.
of course. Like you can't find no other cube with the other color, right? So, but you would not be able to do this trick if I gave you this bag, because you would have no information about the statistics and probabilities and all things. So that's what differentiates me about being able to do this kind of thing. And now, it helps. It's a nice segue to something called Bayesian probabilities or Bayesian theory, where this is all about these things. So if I talk and I have some marking here, we're talking about this a lot. Like this notion is probability of one thing while other thing is true. So in this particular case, what's the probability of object being red when the object is cube? It's 1, like 100%. But we can also do it the other way around. If I have red objects, and what's the probability of it being a cube? So I have 3 cubes, 1 sphere. So it's 3/4 the probability. So it's one kind of misleading thing about Bayesian theory is that probability of one versus the other is different when you switch the directions. And that's I will maybe sometimes still use this as the visual representation of that, because it makes it easier. So we're not talking about objects and colors. We'll be talking about symptoms. I mentioned the health data on the OpenShift, and that's basically some property that you have or don't have, which we call a symptom. And I will not talk about OpenShift alert per se, because it doesn't tell you much, but I will talk about something closer to humans, which is the human diseases. I'm sorry about the topic, I was not able to figure out anything more positive. Not that being tested positive. Anyway, so we have some patients here. Data set that I just created for this occasion, where how to interpret this is that I have, for example, 10 patients that are or have positive flu test and have this set of symptoms: fever, cough, headache, We have also some lucky patients that have flu, but no symptoms. We just happen to test them positively, but they are completely fine spreading the thing around. We also have some, I think I included some unfortunate person that had chickenpox and all these chickenpox symptoms, but he also broken his leg. So double unlock there, but I included there just to show that we could have multiple reasons for the symptoms at the same patient. We want to be able to spread that. So in here, like we can reason about the consequences of flu and fever. And how it relates to the OpenShift is that in the OpenShift world, when you have just a stream of alerts, you don't have any metadata saying DNS is down, you can expect something, some component or some container being broken. We don't have this metadata. And the task is, can we find these relations based on the statistic data that we have? But back again to our data set with our patients. So how we can find some or start reasoning about the relations between different symptoms. So we'll be using this Bayesian theory here, where we'll be looking at the probability of one thing while the other thing is happening. So in the first thing, we'll calculate the probability of having a fever when you have a flu, right? So it's probably not that surprising that if you have the flu, there's high chance that you have fever in that occasion. So when we are running that in our data set, basically we need just the number of patients that have both fever and flu. That's basically in this. It's the number of red cubes, red cubes, and the flu. All the patients that are flu, that is the red thing. So we have red as a flu, and subset of that is the fever and flu. So this red and this cube, so it's the denominator, and the denominator is the whole set of objects, so in this case patients with flu. So it's nothing else than just looking at number of patients with fever in a set of patients with flu. And we get about 60% based on this synthetic data set. So it seems that it's kind of related, but we can't tell for sure yet. Why is that? We don't know what's the probability of fever in the whole population. Like in this case, it would be probably intuitive to say that probably only a few percent of the population has fever, but if the fever was set with threshold 36 degrees, I would not tell you Fahrenheit, I'm sorry, then basically everyone would have it and it would be useless for our analysis. So it's still good to calculate the probability of the fever itself, and then we can compare these values. So what we did here is something that's called likelihood ratio, and at the top one we still have the probability of fever when you have flu, it's this 60%, and we compare it to the probability of having fever in the whole population. And we get some number which, if it's higher than 1, there is some sign that it's significant, there is some relation, there is some correlation. So the higher the higher the number is, the more these things are correlated, right? So that's good. What I mentioned there is that in the OpenShift world, we don't really have the information about the relations, like what's causing what. We have just symbols of individual components. So is there some way to set this direction, like compare it? Maybe what if we switch the order, right? So if we look right now about what's the probability of fever when you have flu, and then compare the whole population, we can also try to switch it around. So taking the probability of flu while you have a fever, just for the fun. So again, like nothing new. It's really almost the same as the first one. We just really switched the order, or basically we just switched the denominator. And we have different numbers, so the results is different as well. There's still higher probability of having flu while you have fever, like nothing surprising about that. And we can also calculate this or compare that to the whole population probability of the flu, which is this ratio. So we have different numbers here, 0.6/0.23, and now we have 0.47/0.18. Now the question is, like, what's the result value of that? So I will get that, and it's almost the same number. It's not the same number just because I was rounding the numbers while doing this, so that it doesn't produce too much output. But basically, these two values are the same. So we took different directions. We look at the flu versus fever and fever versus flu. We even had different ratios, but then when we calculate that, we ended up with the same number, which for me was surprising. Then I look at Bayesian theory and all this, how it works, and it has to be this way. So the conclusion is that this is symmetric. These numbers are symmetric and doesn't give us any indication of the causality, just for this reason. So when people say correlation is not causation, one of the reasons for that is many times when you calculate these correlations, they are symmetric, so you can't tell much more about, can't reason much more about it.
So just so I understand it correctly, is that an artifact, the fact that the numbers are the same, is that because, is that always going to be the true when you switch them, or is that because of the way that this data happens to be, and that's how
it's always the way.
Always the way.
You,
Right.
you
That's
can
mathematical
yeah,
fact.
you can really prove it just with Bayesian theory
Yeah,
and nothing
yeah.
else.
Okay, thank you.
I don't have enough time to do that, but it's fun for sure. So it will not work for us for the reason, but we can compare different things. And I will repeat, like what we compared before is having flu while fever compared to having flu without any other conditions. We can also formulate it differently or use different comparison mechanism, which is probability I have flu while I have fever compared to I have flu while I don't have fever. There's a difference. I don't compare it to all the feverness or flu-ness. I compare it to the flu while I don't have a fever, which is something that I've learned later. It's called relative risk. Because first I just was making up some terms. So if you search for it, it's relative risk. So probability of flu while I have fever versus probability of flu while I don't have fever. So we'll calculate that. So this is flu while I have no fever. Again, no really surprises that it's not that high number because there are many patients with other symptoms that is neither flu nor fever. So probability of having flu without no fever means you need to have other disease, and they are not so common. So we ended up with 0.9 probability. And we can do the same the other way around. No, we still we compare the original probability. I had the flu versus fever compared to flu and no fever, and we ended up with a different number. So basically, this is equivalent of our first equation in here, where we were comparing two probabilities. Now we have just a different coefficient. So it's so we have flu versus fever and non-fever. And now we can do the same for fever versus flu. Again, I have different ratios there. The question is, will they be the same? And if they would, I would probably not give them this presentation, right? So they are different. Now we see that flu compared to fever has 5, and fever compared to flu has 4. So, okay, it tells us something. So this is basically where static thinking can be used this to actually indicate the causality of the problem. So that's the pretty much about the theory, and the assumption is that the higher the score, the closer the symptom that it's at the first place there is causing the whole thing. So I prepared also a function that is calculating these values in table so that you have all these numbers in one place, and we see that flu has higher relative risk than the fever compared to flu, so we would indicate that flu is causing the fever. also I can show this for the likelihood ratio. Basically, you've seen this 2.58 number. It's this one. So basically, we can compare, and you can see really here that this is symmetrical. So you can't tell much about this. So how this actually works? So it's nice to have some synthetic data set, and it just worked. So, but we want to understand how it works. So I have here a simplified data set where I have still patients. I have 10 patients with flu and fever. I have 10 patients with flu and nothing else. I have 10 patients with fever and nothing else, and I have no other patients. So would that work in this case? And it doesn't, because it can't. And why it doesn't is that we even have lower relative risk when it comes to flu and flu. Right? But just because the symptoms are called this way, but the data are not really real, it just will not give us the correct answers. So one thing that this approach really needs is quite good data. And first of all, you need some other examples, some negative examples that don't match neither flu or fever. So I will include some patients that don't have these symptoms. And now we start seeing some correlation between flu and fever, because otherwise it can't reason about the probabilities, because it doesn't know anything about how common fever or flu is. And the other thing that we also need is some disbalance. So right now, it's still showing similar correlations, because we have 10 patients with flu and fever and 10 patients with flu and nothing at all, so it can't reason much. So, but we can increase the number of patients with flu and fever, and we can also include other reasons for the fever other than flu. 50. And now it starts showing up. Now we see that flu relative ratio to fever is much higher than fever versus flu. So there is you need other reasons for the fever to be in the data set to start being able to reason about this. It's not that different from how all these fancy large language model work. They need a lot of data, a lot of examples to be able to deduce the probabilities. It's much more simplified in this way, but you still need data. And on the other hand, you can also use this as a test to tell whether the data you have are really useful or not. You can just have garbage in, garbage out. You can't do much about it. So that's some experimentation with the data. And now, can we do it for the whole data set? I was comparing just the flu and the fever, but I had the chickenpox, I had the broken legs. I want to see the holistic picture. So I have prepared this table, so you can see the relations, right? It's clear. You are not data scientist. So let's do something. So this is basically the graph representation of that. Basically, we ignored the low relative risks. We just don't put line between headache and a broken leg, because the relative risk was just below 1 or below threshold. And we include the lines between them. And you already see some components in this graph, and you can apply some graph theory there, where rash, chickenpox, and fever could be considered as one common thing. Basically, all things are related. In graph theory, I learned that it's called click, or something like that you can search for these components. Similar, fever, flu, cough, sore throat, even headache is somehow related, and it's connected to tiredness. We have on the broken legs and bones part, we have this whole component that is related to pain, because I said the data set to be this way. So, but I was talking about the causality. You see no arrows there, so I was still ignoring that part. But we can also draw the arrows. Draw the arrows there pointing the right direction. And now we have the directions. When the direction means we think one is cause of the other, so the symptom is pointing to the cause. And you can see the chickenpox and flu here are the only balls that are points that have already incoming arrows. So everyone points to those directions, which is in my opinion, kind of magic. So I'm not saying it's perfect. It still relies on how quality data you have and all these other things. Things are not that simple. This thing can do combining multiple symptoms and how they differentiate things. But there are some properties of it that are also much nicer, such as it doesn't require any GPUs. No GPU was hurt. And you can still run it on GPU if you can't wait for 5 minutes and you want to have it in 1 minute or so. But it's much easier to do. You can also, if you compare it to the machine learning algorithms, it has some benefits as you can really reason about it. It's still some numbers that you can put some meaning behind, and you can iterate fast and basically understand how good you have or your data have. I mentioned the columns limited power. So the conclusion I would say for that is that you should be using both. Don't be shy to use both. Don't be shy to use stats just because machine learning is cool. But I noticed that this boring guy is proposing machine learning and the cool guy is proposing stats. So that's pretty much what I wanted to, the message I wanted to give here. And the last thing, just if you hear data science, don't think about that's the job for the data scientists, because I've seen that it's valuable for subject matter experts to do these kind of things and complement this whole area with some knowledge about the field itself, and we really don't need to be rocket science to do this kind of thing. You can look at me as an example of that. So with that, I guess we are running almost out of time. So thank you very much for your attention. And I will still have maybe 3 minutes for questions. So now is the time to do that. So questions? Do you want to have more tricks? Because if you do, I can't help you.
Okay, so
Oh, there's one question.
Like, what are some real examples where you were able to use this and like get to root cause analysis? Were you able to
Great
are you able to
question.
show us some examples?
Great question. And actually, we have not, we were not planning this, but I have some real example here. It's not about the root cause. It's still something that I need to apply to the real world, and we've seen some of these indications. But when it comes to the clustering, like grouping the things together, this is some real data where we have some cluster where it has some issue here, which you can see had multiple different alerts. We don't really want to reason much about that. We can do some time grouping, which is just grouping the things together based on the time that appeared, they started happening. But then we can apply this additional contextual grouping, and I will highlight this particular group. And I will also do this thing. So when we did the time grouping, we had these etcd members down and Brazilian other alerts, but there was some noise introduced there because some other incident was just happening at the same time. When I include the additional contextual grouping, it's now split into two things. So we still have the etcd members down, but then we have the pod security violation that was not related. And just for the statistics that we had about that, we could actually separate those two. So that's basically the area of applying this kind of approach for the real world, not just for playing around in Jupyter notebooks. Thank you for the question.
Engineer in Red Hat, currently on the DBZim project, and I'm moved into this role from being actually the former UA lead for DBZim. So we will have a brief look at what change data capture is, then of course we will focus on the DBZim project, and from there, because we are supposed to focus on non-relational databases, we will talk about change data capture for MongoDB specifically. And after that, we will actually have a look at one of the possible use cases for change data capture, tiny demo. At the end, there will be place for questions and hopefully some answers. So, what it is, change data capture? I very much like this definition that change data capture is a process of recognizing changes in a data system and their delivery to some downstream consumers so that these consumers can take actions based on these changes. This diagram actually portrays one of the variation of change data capture. This is based on mining of the transaction log. Is somebody here who doesn't know what a transaction log is? Okay, so just for the remote audience, briefly, a transaction log is sort of a canonical source of truth for each databases, and that's the thing which actually records all the operation and all transactions, which then can be used, for example, to recover when something nasty happens to the database, for example, some outage or anything like that. So we have a database and we have some users which are actually executing all your regular create, update, delete operations and modifying your data. Then we have a CDC platform which is reading the database's transaction log and it's emitting events about these changes to any possible downstream consumers, which can then, for example, store the events as data in some data lake or data warehouse, or perform some calculation and statistics on top of that. Besides this transaction log mining approach, there are some alternatives. Mainly, we can implement a CDC based on queries and based on database triggers. However, these approaches do have some disadvantages. For query-based change data capture, one of the obvious disadvantages is that you have to constantly execute your queries, so that puts additional strain on your database. And you are also not able to actually capture all the changes, because how do you actually write a query which captures deleted data? The answer is you don't, you can't. With triggers, you can actually recognize all the changes to your data, but you get a very database-specific implementation, and you are also limited by the expressiveness of the procedural language which is supported by your database. So you might have actually issues getting the changes out of the database. The most common use cases for change data capture include, but are not limited to, things like data replication or actually cache invalidation or search and index updates. You can also build auditing on top of it. And last but not least, you can actually use CDC with microservices to implement some of the architectural patterns, which we will have a look at the end of the presentation. One of these things is like reliable data exchange between microservices. This brings us to the DBZim project. So what is DBZim? DBZim is actually an open source, complex change data capture platform which covers multiple databases. We have quite active and large community because the project has been around for a while, and it's been used in some relatively large scale deployments by our community already. When I said that we support multiple databases, we have to talk about so-called DBZim connectors, and these connectors can be actually divided into three different groups, so to speak. First, there are the core connectors. These are the connectors which are, the source of these connectors is actually part of the main DBZim repository under the DBZim organization, and these connectors are developed, maintained, and supported by the core DBZim team. Then we have community connectors. Again, these connectors are housed under the DBZim organization umbrella on GitHub, but they live in separate repositories, and they are actually developed by our community contributors. So for these we have DB2, Cassandra, Vitess, and our newest addition, Google Cloud Spanner. The third group, which for me is probably the most valuable one,
are independent connectors. These are connectors built by completely third parties and different companies outside of Debezium team and Red Hat and everything. And these are built on top of our common CDC connector framework. So to me, this really showcases that the project kind of took a life on its own, and it's now spread beyond the boundaries of our core team and Red Hat in general. So how can you run these connectors? First and foremost, our database connectors are actually an implementation of Kafka source connectors. Do we have somebody who doesn't have any experience with Kafka? Okay, so Kafka is, let's say, event messaging platform, and there's this component called Kafka Connect, which provides you the ability to run services or connectors which can get data either into Kafka or out of the Kafka. The ones which are getting data into Kafka are called source connectors. So that being a Kafka Connect connector, it means that it actually requires Kafka and Kafka Connect to run, and the events are then stored in Kafka topics. So you can deploy Debezium as Kafka connector on top of Kubernetes using the Streamz operator. Hi Jakub, you are just in time. The other option is actually embedding Debezium into your application through something we call Debezium Engine. Debezium Engine actually started as a tested dependency because we needed means to actually prove that the connectors work. But as it's usually with good testing tools, they kind of became used in production by some of our community members. So we've decided to improve it, and we've actually built another runtime around this Debezium engine, and that's how Debezium Server was born. Debezium Server pretty much fulfills the same role as Kafka Connect does, but it's simpler, more lightweight runtime, and it's really meant for different data sync architectures where you either don't want to or can't use Apache Kafka. We also support many other things besides actually being able to store these events in Kafka. You can get them into Amazon Kinesis, Google PubSub, or simply send them over HTTP. The new addition to this ecosystem is the Debezium operator, which was just released in the first preview version, and you can actually use that to deploy easily Debezium server on top of Kubernetes as well. Now to the third important part of this talk, we also need to say what MongoDB is, because that's going to be the database of focus for today. MongoDB is a document-oriented NoSQL database. NoSQL database, that means that it doesn't deal with relations, similarly as, for example, MySQL would. And document, it means that the data is actually stored in form of documents. Other than that, there's a pretty similar structure to the database. So you have the database itself. A collection would be an alternative to what the table is in relational databases, and the document would be a counterpart to a row in that table. The documents themselves are stored in a format called BSON, which is a binary representation of JSON. However, it's not just binary JSON. BSON goes beyond what a regular JSON is. For example, there are additional data types which are supported in BSON which you wouldn't find in JSON. And MongoDB also has native support for change of the data observation. Before we actually get to extracting the data, we need to talk about how the database can be run. First and foremost, there is this standalone deployment, but that's not really meant for production. It's recommended just for testing and development environments. And since there isn't any way to actually extract the data changes from standalone deployments, we don't care about it, and we cannot possibly cover it. So that leaves us with two: a replica set, which is the basic unit of MongoDB deployment. It provides some basic data redundancy and HA features. And then if you want to achieve horizontal scaling of your data, you can use MongoDB sharded cluster deployments. The primary one is a replica set, as I already said, and it's a typical primary secondary topology where you can actually see that we have a client, and first of all the writes are always directed to primary, which holds the data, and the data is replicated to secondaries, which acts first as a data replicas, and second they can actually take off some of the load from primary to support reads from the secondaries. So that's the basic topology. If primary goes down, then the secondaries are actually entering election phase, and they will among themselves elect a new primary. This is done by the fact that there is a heartbeat going on between all the replica set nodes, which means that every node in a replica set is actually aware of the existence of all the others. The data replication part is actually the core of what we need to know for DBCM. As you can see here, we can see some data copying going on, and this is so-called operations log. At the beginning, I've talked about databases having this transactional log, and this is actually an equivalent in MongoDB for this. So what is an operation log, or OBLOG for short, in MongoDB? It's a capped collection holding a rolling record of data modifications. What does that mean? Well, first, as I said, what a collection is an equivalent to what a table would be in a relational database. And what it means that it's a capped collection, so it means that there are some restrictions of it, on top of it. And OBLOG specifically can be restricted in two ways. First, there is a maximum configurable size of all the data within the OBLOG. And there is also configurable time retention in hours. If the OBLOG either grows very large outside of the maximum size, or a record is in OBLOG for longer than is the maximum retention time, then entries will start dropping out of the OBLOG, and these actually mean that the data will be lost. So, long story short, OBLOG actually keeps all the changes done to the database for a specific period of time. So, depending on the configuration, the size, and the retention of OBLOG, that's how far back in time you can actually go to replicate all the changes which were done through primary. And this OBLOG is actually the means how data replication is achieved in replica set deployment for MongoDB. So if this secondary 2 replica went down and the primary had an OBLOG which is configured to retain data for 2 hours, for example, then as long as the secondary would be back up in less than 2 hours, it could just really stream all the required changes. If the secondary was done for longer than 2 hours, then it would have to discard all its data and actually copy everything from the beginning. For sharded clusters, it's where it starts getting complicated. We have to first add a component called Mongos, which is the Mongo router which decides to what shard you want to go, and then we have separate shards. But first, what actually sharding achieves is a means to horizontally scale your data. So it means that if you have, for example, a customer collection or order collections, then a portion of the data is actually distributed to each of your shards. And the Mongo router is the only part which actually knows about all the specific shards. So that's sort of a glue layer on top of regular replica sets, which decides where queries be routed, or how to merge search results, or perform sorting across these shards. Because the shards themselves are individual replica sets with individual operation logs. So they are not aware of each other's existence compared to the nodes inside of replica set. Getting the changes out of this OBLOG can be tricky sometimes. So since version 4, MongoDB actually provides an abstraction called change streams. This is a feature where you can actually subscribe or open a change stream against the database, and the database itself will push information about these changes in form of change stream documents to the client. And this is the feature which DBZoom actually employs to extract these changes from MongoDB. You can actually start the change stream at some operational time, which again can go as far back as is the maximum retention of the OBLOG, because change streams are still just an abstraction on top of OBLOG, Or when you actually get some change stream document from this change stream, you can use its ID as the resume token to start receiving these changes after a certain operation from the past. How does the entire change extraction process function with Debezium? Well, first in Debezium we have these two phases. First phase is something we call snapshot. That is what at the beginning we actually query and transfer all your data into events to actually get the starting point. Before we do that, the first thing we do is we actually obtain a resume token. So this is the point of time where we started the connectors, and from there we will actually stream all the changes. But before we start streaming, we transfer all the currently persisted data into events. Once this initial data copy phase is performed, then we switch into what we call a streaming phase, and that's where we use this formerly obtained resume token and open a change stream and start streaming the data. With each change document we receive from the open change stream, we do two things. First, we actually transform it into event and we deliver it into the sink, which could be Kafka, Redis, HTTP, Google PubSub, or any other messaging system we support. And we also store the resume token for this particular change into our offset storage, so that in case there is an outage, for example, there is a connection loss to the database, we can resume streaming from that point of time. Once again, I've mentioned change streams being an abstraction on top of operational logs, so that means this offset can be at most as old as is the maximum retention time for change streams. In case you actually, for example, have an oblog which retains changes for 2 hours and your connector is down for more than 2 hours, then when you restart the connector, depending on configuration, the entire process will happen from the beginning, and you will again have to undergo the initial copy of the data, because otherwise you would be risking data loss, and this is something we cannot guarantee. Or we cannot guarantee, don't want to, we want to guarantee the exact opposite, that you don't lose events. It's a bit more complicated when we get to sharding, because in this case we have two options how to actually extract the data. In both cases we are opening change streams, but in the so-called replica set connection mode, what we do is actually, in order to achieve higher throughput and higher performance, we open an individual connection to each of the shards within the sharded cluster. This has the advantage of having larger throughput because we stream changes down to each of these shards separately, but it also means that we can never actually guarantee, for example, the order of changes performed across these shards. We guarantee it always if there is for example, if there is a new entry which we are observing, we can guarantee that all the changes will be in the right order for one specific entry, one specific document. So you will always get creation first, then there will be modifications in the right order, and if you delete it, it will be always at the end. Is there a question in the background, or? Okay, so we can guarantee the order of these changes for one particular document, but we cannot guarantee the order across documents, because there is no means of actually knowing for Debezium whether a change in shard 2 occurred before or after a change in the shard 1. We can have these guarantees in the other connection mode for sharded cluster, which is called sharded. In this case, we open the change streams against the Mongo router, which glues everything together, because the Mongo router in turn opens change streams to each of the shards, and it performs a synchronization and it orders everything as it should be. But the price for it is that there is some overhead, and then there is some delay before you actually can get these changes from all of those shards. So this is all a theory, but let us look at how we could actually approach some practical problems using Debezium and MongoDB. So Imagine we have a simple order service which needs to do two things. First, we need to store an order, and we also need to send a message to another service called shipment service. And we need to do all of that reliably. What's the problem? Well, dual writes are prone to inconsistencies. So if you want to guarantee that we do both of these things, what's the first solution which comes to your mind? Any ideas? Well,
At the same time.
What?
At the same time.
Yeah, well, not at the same time, but sort of both or none.
Yeah.
You have to guarantee that both succeed. Well, distributed transaction and two-phase commit would be an option, but first of all, you may not want to use distributed transaction, and for example, if the system where you want to send the message is, for example, Apache Kafka, it may not even support it. So how do you actually ensure that if you store the data in the database, then the message is always delivered as well? The solution is something called outbox pattern, and it starts with actually eliminating one of these external systems. And since the database belongs to the service, the one system we eliminate from this process is sending the message, or eliminate, we move it somewhere else. So instead of initially sending a message, we save a message into an outbox collection together with the original order, and we do both of these inserts in a single document transaction. That means that we eliminate the service coupling, but then again we still haven't sent the message to the Apache Kafka, so we need to introduce sort of a worker process which will be responsible for delivering of these messages. The way it will look like is that we will have this order service that stores both the order and the message, and then we need some thingy which will read these messages and guarantee that they get delivered into Apache Kafka. So what's the process for the worker thingy to actually send the message? First, it needs to poll the collection and check if there are any unprocessed messages. So it gets a message, then it needs to send the message, and then it needs to mark this specific message in this outbox collection as processed. What are the weaknesses of such approach?
Latency.
Yes, you cannot guarantee that you actually do this near real time, and then you again are polling the collection, so you have a similar problem as you would have with the query-based change data capture approach, and you can't really solve the fact that in order to reliably mark it as processed, you would have to again do both of these in transaction, the sending of the message and marking as process. This is something which cannot be solved, so the best we can do is actually have at least one guarantee. We can guarantee that each message will be processed, but we can't guarantee that it will be processed more than once. And last by no means least, if you are the developer who is supposed to implement this pattern, then it requires a boilerplate. You've gotten from sending a message to implementing an entire worker process which has to query a database, send message, and ensure that it does it reliably. That seems like a lot of work. However, this is actually where DBZium can help you, because it gets rid of the entire need to implement this worker process responsible for delivering these messages. You just plug DBZium to your database, and it will completely act as the worker process. It will be observing any changes by opening the change streams to this outbox table, and it will be emitting these messages to a desired Kafka topic. There are several mandatory but configurable parts which these messages need to have. So we need something called an aggregate type. This is just purely to distinguish different message types. Then we need some ID of the related object to this message, and then you need to provide some payload, which is any data or non-data which you wish to send with this message. Then there are additional fields which you can add as you wish. For example, in this case, I have a field called type, which distinguishes the type of the event. Let's demonstrate with a simple demo. So first of all, I have a local Kubernetes cluster running where I have three things. First, I have a Kafka deployed through the string operator. I have some tooling image which provide us with things like Kafka Cat to actually have a look inside the Kafka topics, and I have a Mongo database running, and I also have a database operator. First thing I'm going to actually do is deploy Debizium, and before that happens, we can actually have a look at what is the configuration. So this is the configuration for Debizium, and we can see three important parts. First, we have this sync configuration portion, which says that we will be actually sending these events to Apache Kafka. If we wanted to, we could replace this Kafka configuration with, for example, Google PubSub, and the messages will be emitted to Google PubSub. Then we have this source configuration, which just unsurprisingly configures a MongoDB connector because we want to extract these changes from MongoDB. And the most important part for us is actually this transform part, because the outbox pattern support is implemented as data transformation. And it's again really simple. It just says that we want to use this Mongo event router. This is a configuration to which topic we want to actually send these messages. So in our case, it will be events dot and then a name which we will configure as the aggregate type. Then this additional configuration just says where the type field should be placed, and that we kind of want to unwrap our data to actually get rid of some Debizium format envelope which we are using for other messages. So in the meantime, it looks like Debizium actually started. So first we will actually simulate what a service would do with the data. So we will open a Mongo shell connection, and we will just demonstrate that there is no outbox collection yet. It's not there. Okay, there are a couple O's, but it's not there. And I have a simple JavaScript code which will do a simple simulation. First of all, we will open a MongoDB session, and then in a transaction we will create a new order, and we will also create a message which will just contain this order as its payload, and we will store both these in transaction. So now we've stored it, and we can have a look into Kafka and see whether we've actually received these messages. I will just connect to Kafka. I want this mode. I want it unbuffered, and I want a topic. I want it to go from the beginning, and I'm going to topic name events order. And just to have it look nice, we will pipe it through. Yeah, and so we can see that we've received this message, which in this case we are able to show just the payload. But if we looked at the entire Kafka message, including the message envelope, then we would get a slightly different output. And in this case, you can see that in headers we also have this order created value for the type field. If we were to cancel the same order, again I will cheat a bit and copy it from here. then you can see that we've actually received another message, and in this case the payload is empty because we haven't stored anything. In this case we are just cancelling the order. So the takeaways from this is that CDC is a quite useful tool in event-driven architectures. Debezium is actually a project which provides the means to employ chain data capture, and Andos pattern provides efficient means for microservices to actually reliably exchange data, and is an alternative to distributed transactions and two-phase comments. If you have some questions, I will try to answer them.
It's still at least once delivery though, right?
Yes.
Anything else?
Although specifically with Kafka, and that's something Vojta here would know more about, there is now a possibility to have exactly once, right?
Yeah.
But that's specific for Kafka at this moment, because Kafka is the one doing the deduplication. Okay, if there are no more questions, I thank you for your attention. And if you want to ask something off the record, I will stay around for a while.
Hey guys, wrong. And I'm gonna close the door.
Hello everyone. I think we have a full room. We didn't expect it, but we're really happy. So my name is Katja Bardeva. I'm principal software engineer at Red Hat.
I'm Sandia, software engineer at Red Hat too.
And today we're going to talk about how we wanted to implement a machine learning model, but went ahead to production with a simpler statistical model. So this is the agenda for today's talk. So we're going to talk about some possible challenges you might face when training your model. And then even after you have a model trained, you still have a long way to go to bring that model to production. So we're going to come back to that slide at the end of the presentation. So if you've been following AI news and papers in the last 5 years, you might have noticed that there's a lot of information about the algorithms themselves, but there is way less emphasis on the data. I would say in the last year, the emphasis actually has shifted to the models, which is both the algorithm and the data. But there's still a lot of information about that. So today we wanted to talk about same algorithms with different data will perform differently, solving different problems. So we don't want to talk about the algorithms themselves because there's a lot of information about that on the internet. We want to focus on the challenges that most people would face trying to bring it to production.
Yeah, we are going to tell you about our experience. So we're going to give you a bit of context. We are part of OpenShift, which is an enterprise solution written by Red Hat. Probably most of you know about it. It's basically for operating containers. What we do is getting a bunch of data from our customers' OpenShift clusters. We process that data and generate a couple of graphs, notifications, emails, and recommendations for the customers to better manage their clusters. The last project that we participated in is the upgrade risk predictions, update risk predictions. It's the project that we are going to talk about today. It basically predicts whether an OpenShift update will break the cluster or not. That's the point. So before starting with a machine learning model, you first need to make sure that you understand the problem that you are going to solve. Otherwise, you will be completely lost.
Let's talk about the problem statement first. So first you need to identify what is the actual problem your model will try to solve. So operating in a system, as you know, comes with a cost. But it's even higher cost getting that system out of a failed state. So because you have time urgencies, you have the user screaming at you, so it's usually very expensive for the brand, with money, and for the people. So these are some examples of real-life failures. So for example, imagine having to deal with a water leak on a Monday morning when you need to go to work. Or an airplane engine failure during takeoff. So another example, I'm not sure if I found the right icon, but this was supposed to be tsunami or an earthquake. So tsunami or an earthquake in a highly populated area. And this one is an example for a bridge collapse because there are either too many cars or it was unmaintained. So all of these can be mitigated or monitored. For example, airplanes usually have regular inspections for everything, like engines, landing gear, and so on. The same for bridges, but for example, for earthquakes and tsunamis, we have monitoring. So usually some scientists or knowledge agencies will send forewarning when they detect some shakes. So it's way cheaper to try to prevent failure than deal with the outcome of that failure. it can be expensive both with money and, as we see in airplane, earthquake, and even the bridge collapsing example, it can cost human life. So we're not going to be that, so we are not dealing with human life factor, but we try to save the money for our customers. So some examples closer to home, since it's DevConf. For example, imagine a service failing to serve requests because it's out of resources. So you can mitigate it by setting up monitoring that will automatically scale it up and down, or you can use Kubernetes. Another example is you try to deploy a new version of your software, and then late in the process you notice that there are some failed dependencies. So you can use tests, end-to-end unit tests to detect that sooner, CI/CD, or you can use stage environment, or you can use all three of them if you really want to prevent these kind of failures. So let's think about modern cars. So modern cars are both combination of hardware and software. Increasingly more, special example, I think everyone knows, is Tesla. So they have hundreds of sensors in those cars measuring everything. And those cars, they send a lot of telemetry to the manufacturer. So example of those sensors is if they can measure the state of the battery, the state of the brakes, the tires, if there are any oil leaks, what is the oil level, and so on. So there is a lot of that information. We probably have here people from different countries. Probably in every country there is a car checkup. So when you bring your car to some government-approved agency where they check your car and tell you if you're allowed to go on the streets or not. So usually there's like once a year, once 4 years, depends on the age of the car, at least in Spain. So the way that car checkup goes is you take half a day of work, you drive there, you wait there for 2 hours, true story. Then you go through the car checkup, and then at the end of it, the engineer says, well, your brakes are not really working, you have a problem with discs, or you have ball tires. So after that, you take your car to the mechanic, you fix it, and then you go for that checkup again. So basically, you have days of your time wasted that could have been prevented if there was proper monitoring for the car. So what if we could do something different? What if your car were able to tell you if it's going to fail the checkup and what is that you need to fix before you actually go for that checkup? Or closer again to our example, remember what Juan was showing, our application was we wanted to predict the upgrade failures for our software. So what if we could predict those upgrade failures? Because after an upgrade has failed, it's usually an emergency, especially if it affects customer workloads. So a lot of people need to jump in, spend a lot of time, and yeah, prevent damage. So what if we could predict those upgrade failures?
So now that you understand the problem that we are trying to solve, every machine learning model depends on the data set you have. So the typical data set that you will have for machine learning projects looks like this. This is an example from a typical problem. It's about predicting the sale price of a house based on the size of the house and the number of bedrooms. If any of you have tried Kaggle, you probably tried this problem. In machine learning, you have features and labels. The features is the data that you have in the real life, and the label is the data that you want to predict. In our case, we have a bunch of alerts and issues, and we want to predict whether this will make the cluster fail or not. So, apart from the problem statement, the data set, make sure that you are bringing some business value to the company. Otherwise, you're just spending resources and money and not bringing anything valuable for it. So, these are the 3 steps you have to follow before starting a machine learning project. We'll continue with the rest of the path.
And this was just the beginning. So you identify that you have a problem, that you have some data to try, and it's probably worth at least researching how to solve it. Then after that, you have a go-ahead from, I don't know, someone in your company saying, okay, we're going to spend some time solving that issue. You will have to train a model that solve, you would have to train a model that actually resolves the user's problem, and then you still need to bring it to production. So there was a talk earlier in this room where they showed that actually when productizing, the code for the model itself is like 10% of the whole pipeline. So let's talk about model challenges. First thing, before you actually write any code, well, you can try playing, doing some EDA, but we really recommend to think what does success means to you. So what is the definition for success for this project? So we think that it's really important to get your business folks, your customer-facing people, your data scientists, engineers, ML people, so anyone that would have to participate to make the project successful, to get them into the same room, and don't let them out before they agree on the acceptance criteria for the project. And bring pizza, because it will take a lot of time. Then you have to agree on those acceptance criteria. So as you have probably heard, AI, ML, it's all the hype right now, but under the hood, what it actually is, it's just creative math. So it needs some optimization mechanisms, metrics, for the model itself, for the algorithm to understand the worse and the better outcome to use it for the next training iteration. So the choice of a metric, so we're not going to talk too much about metrics because it deserves its own talk, but in our case, and in general, your choice of metric will depend on the problem that you're trying to solve and the data that you actually have. So in our case, we have way more upgrade successes than upgrade failures, thank God. But we also don't really care about predicting upgrade successes because, well, it's like with car checkup. Who cares that it's successful? We really want to know when it fails. So we have an anomaly detection type of problem. So we really want to identify upgrade failures. What we really do care about is we really care about minimizing false positives. I used this icon for minimizing. We really care about minimizing false positives, and we somewhat care about minimizing false negatives. I know these are fancy statistics words, but what it means is, in this case, so we're trying to predict upgrade failure. False positive is we predict that the upgrade would fail, but it actually succeeds. And false negative is the other way around. So we predict that the upgrade would succeed, but it actually fails. The reason we really care about false positives is if we predict that the upgrade would fail, but it actually succeeds, it brings, it can hurt our brand, our perception of our product by the customers. They're like, we see that in your portal that the upgrade is going to fail. This is your product, so you're kind of responsible for the upgrade of that product. So it might hurt us as a brand, as a company. And the other reason is it might discourage the customers from upgrading to the latest version. And we really want them to be on the latest version. The second one, false negatives, we still kind of care about that, but with Kubernetes, we have accepted that it's not always possible. So false negatives is when we predict that the upgrade would succeed, but it actually fails. So we cannot predict all the configurations that people use for Kubernetes. So they can use different cloud platforms. It can be on-prem. We cannot control the DNS setup that they have. So we cannot predict all 100% of the failures. So we accepted that, and we really try to minimize. So we try to be really precise about it. So I also put here the official, the names for each of those metrics. So we really care about precision. We somewhat care about recall. If you've, I don't know, taken some statistics classes before, you might know that they are related to type 1 and type 2 errors in statistics. So do we have AI, ML enthusiasts here? We didn't want, we were debating if including this slide or not, but because we try to avoid fancy, long formulas, because we wanted to keep it really high level. But essentially this formula is the expression of this. we care about precision more than recall, and this formula expresses, so this is F-score, and here, by choosing 0.55 coefficient, we specify, this means that we care about precision twice as much as about recall. So this is our chosen metric for this project. And it's always easier, it's always better to have one single metric to guide your project, because you cannot train a model using several metrics, because it needs to know what it has to optimize for. Then the next step is you need to create some sort of baseline. So it can be either some crude heuristic, so you can use a script that is using some assumptions, so it's not machine learning yet, but you're identifying the acceptance floor and ceiling for what is actually possible out there. You can also use humans, like human labelers, to see what is possible. One example is, we've all seen this before, reCAPTCHAs. So before, you usually use some either API. Last time I've seen it was a couple of days ago with ChatGPT, when they ask you to identify, what do you see in this, find all the bicycle, boats, whatever. So, but even for humans, it's not always possible to identify objects in the picture. So 100% accuracy is not always possible. So aiming for 100% accuracy for your machine model, is also usually not acceptable. So yeah, it took me a while. So the reason you create a baseline is, again, to establish the borders, so the ceiling and the floor for what is kind of possible. You examine your data so you know what is there instead of just shoving it into some algorithm. And the second one, it either makes or lets you talk with the subject matter experts. So they can guide you, okay, but based on our experience, this doesn't really make sense. So you can create intuition while working through a baseline. And after you have a baseline, you can start experimenting with some automated solutions, so some machine learning model, either pre-trained or take the algorithm and train it on your data yourself. Trying to approximate either the human level performance or beat the baseline, and after that you keep iterating. Throughout all of these steps, it's important to keep the real problem you're trying to solve in mind, because most of the machine learning projects, they take at least a couple of years from the moment of you have an idea to do something and then bring it to production. Usually, your understanding of the goal might evolve, but it's important that you keep talking to the business folks, to someone who would close to the customer, that it still meets what they expect from your solution. And throughout all of this, iterate, go to previous steps, pivot if you need. It can be a long road. Remember, OpenAI didn't stop at GPT-2. They went with GPT-3 and the whole hype of the last year, I think it was November. So they finally delivered something that excited millions of people.
Okay, you may be asking why we are telling this if the title of the talk was about not using machine learning and using an if-else instead. So all that we have talked about in the past minutes is about things that we learn by issues. So now, please tell us the issues that we had.
So we created a baseline, we trained some machine learning models, we defined our metrics, so we did all the homework, but what we found out is that all of them performed kind of the same. So our simpler heuristic had similar accuracy to decision trees, to large language models, and so on. So we had to find why. While we were chasing the reasons why it performed worse, we decided to, since our heuristic worked and we decided to iterate fast, we decided to go to previewed, well not, it's still production, but like a preview feature. We decided to go with a simpler statistical model instead of machine learning model because it still automates things, it brings value, even though it's not as fancy as we wanted. Now the theories why actually many machine learning models on your data may perform the same. actually the reason is usually the data that you have. So we are currently chasing several theories. So one of the theories that we have is maybe the data that we trained on doesn't have enough predictive signal. So imagine with a car example, if you fail a car checkup because your brake discs are worn out, if we don't have a sensor on the braking disc, you will not be able to predict the failing checkup. So we are currently chasing additional signal, probably metrics in this case. So we are performing some tests there. Another one is maybe the data is either not complex enough or not denoised enough. Usually for machine learning models to get an edge over some simpler solution, you need lots of data and it needs to be complex enough for it to be able to detect more subtle patterns. So we are denoising the data set and we are getting more data for a longer time frame to see how it will impact the performance. Another lead that we have, this is like detective work. Another lead that we have, maybe the labels that we have are incorrect. So with the failed car checkup, it's very Boolean. So the engineer says, well, okay, you failed because we performed these 20 tests and this one was failed. But how many of you have worked with Kubernetes before? So as you know, with Kubernetes and its self-healing architecture, it will try to reconcile for a long time. So technically in Kubernetes, there is no concept of failure unless you specifically define it. It's like lack of success for a certain amount of time. So in this case, we decided to treat upgrade failure if we didn't see upgrade success within 8 hours. But there might be multiple reasons why the upgrade can take more than those 8 hours. For example, huge clusters with a lot of worker nodes. The customer may set up disruption budgets that prevent the node from draining. So it's a healthy cluster, but some configuration prevents the upgrade from succeeding with the time. So we are currently inspecting if classifying into upgrade failure, upgrade success is correct. So maybe we should lower the threshold to 4 hours. Recommendation from our upgrade engineers is like they expect the control plane to upgrade within 2 hours. So maybe lowering it to 4 to 2 hours is a good idea. Another idea that we are investigating is maybe we better predict upgrades that went successful without human intervention versus upgrades that required some operator to go and kick in the tires. The problem with that is this will probably help the accuracy, but how do we identify that in the data? The customers are not going to go to us and say, well, I went there and I fixed it manually. So it's going to be more difficult to create a proper data set for that, but we're going to try. So. And the last one is in Kubernetes, some errors are expected by design. So metrics, you will see, for example, from Kube API during some restarts, you will see that 404 is returned from Kube API. And this is normal situation during the restarts. So usually we call them flapping alerts metrics when it's coming up for 3-5 minutes and then it self-resolves. So it's important to either have the algorithm that is smart enough to be able to ignore those fluctuations, or you can pre-clean the data set to exclude those things.
So yeah, we launched it with a rule-based model instead of a machine learning model, and we are not ashamed about it. It was a nice path, and we learned a lot of things. We also didn't refuse to use machine learning at all. We are continuing with the studies, and we hope to have a proper model working in the close future. And instead of stopping, we keep moving and put this model in production because it's worth it. We now have everything in production ready for putting a machine learning model whenever it's ready. So I think
it went off the focus.
Oh. Yeah, so I'm not going to talk about the productization challenges and what we learned during this path. I'm just going to share some advices, but there were many other things. But let's start with communication. It's not just for machine learning projects, it's about any kind of project. if you have many groups working in the same project, many of them will have some issues, blockers, timings, and you have to collaborate and coordinate in some way. If you start coordinating by yourself, it can be a complete mess. You keep adding communication channels, and you end up with this kind of number of channels. It's just a simple formula. But you should take a coordinator, call it the project manager, product owner, or whatever persona. It's really important because it's the responsible of meeting deadlines, making sure that when a team commits for a deadline that it's met, and also for running like weekly meetings or sync meetings, status meetings, so that everyone understands the progress, the blockers, and what needs to be done. A cool way of making sure that everyone understands what needs to be done is with API specs. If you are working with microservices, it's really nice to have an open API spec beforehand, before creating the integration or developing the microservice. Also, you can just use a shared document and put the architecture there and start reading from there. And also, VDB test, which is a talk that is happening right now, so I'm really sorry about it. But it's just writing tests in a simple way with plain English, and then writing some Python magic in the background so that everything is automated and so on. But it's a really nice way of making sure that others understand what you are working on. Second suggestion that we do to any project, you need to choose speed versus perfection. We decided to choose speed. It's really worth it. If you are trying to compete with other companies, you need to be faster than them. And perfection can be achieved in the future. You just need to iterate and try new things. So if this feature never gets interesting from our customers, that's it. We just spend a couple of months and that's it. We released it and it can be a triumph for us, but that's it. Something that helped us with speed is the DevOps mindset. We use an internal Red Hat tooling called AppSRE, many of you might know, that let us spin dashboards, microservices, databases with just a couple of Git repo lines. It's using in the background Terraform, GitHub, OpenShift, GitLab, and it's interesting that it uses OpenShift because we are like collaborating in OpenShift using OpenShift. It's a closed loop. Another really nice tool that we are using are ephemeral environments. It's just a way of spinning up OpenShift clusters, but just for you, not for the customer, for customer-facing APIs. So you just spin up an ephemeral cluster for example, just an hour, copy the production or stage environment, and deploy it in a cluster but connected to your machine, and then you can start coding and testing your changes there. This is useful for locally testing things, but it's more useful for CI/CD. All of our tests runs on real clusters, so we are safer to deploy to production. And the last advice that I want to tell you is scalability. If you want not to touch these services in the future, you need to think on scalability beforehand. What we do is put in a proxy between our solution and the customer. So we call it proxy. For example, it's just a stupid microservice. Just takes the user request and adds some authentication or patching or whatever mechanism you want to add. But then you have the real stuff in the background. You have first the data engineering, which is gathering some data for data enrichment and data engineering. Also preparing the data for the model, because each model may need a different input. And then we have the inference, where we put the model. Now it's running a statistical model, but it's ready for running any machine learning model. And the good thing about this architecture is that everything is stateless. So you can scale it whatever you want. If the number of users increases a lot, you can scale the inference part or the data engineering part. Also, if you want to go with a huge model like, again, ChatGPT, you may need a lot of resources, so you may need to scale the inference part. So it's really comfortable to have something like this. It's simpler to monitor and simpler to scale. So, wrapping up. Sorry for all this talk. Before starting a machine learning project, you need to make sure that you have your problem statement pretty clear. You understand everything that needs to be done. You have the data for training this model, and that you are bringing some business value to the model.
And for the productization part, again, recapping, you need to make sure that all of the teams that you have understand and have the same priorities. Remember the trade-off of speed and perfection. So better go to market faster with something that works better than your competitors or something, then keep iterating so that you can reach perfection later. And same about scalability. Make sure you have the architecture in place to be able to scale. You don't have to implement it right from the start. So thank you for your attention. Any questions?
How many rules did you end up with, roughly?
3 lines of code.
Wow.
That's the logic. Well, the statistical model is 3 kind of longish lines of code, but it was months, weeks talking with subject matter experts, exploring the data, and so on. But it's very cheap to operate. But we're not going to stop there. So.
I'm facing a similar problem, so to say, and we're not started to implement yet. So I wanted to ask you how much time you invested in the machine learning model before deciding to move on with the if-else approach.
We were not alone in this. We were collaborating with IBM research team, so the real data scientists were, so we're engineers. We dabble in data science, but we're with engineering background. So they were working for 2 or 3 months, trying different things. They were trying decision trees because this has to be explainable. That was one of the requirements because we need to tell why exactly the algorithm is going to fail, so what they need to fix. And that's not always possible with machine learning models. So they tried decision trees, which is kind of explainable. They tried foundational models, so the large language models, kind of like GPT. So 2-3 months, and then we made a decision in February to do the first release with a simpler model, and we keep working in the background.
Okay, thanks.
You mentioned that one of the possible failures was that the data set, the training set was not large enough. So can you quantize how big the data set was?
We took the data for the last year. The problem, or well, if we talk to OpenShift engineering, they will say it's not a problem. The problem for us is that not so many upgrades fail. So we had less than 1,000 examples of failure. So it was highly imbalanced. We tried to balance it out by excluding some of the successes or pre-classifying it. So we need to, so if we lower the threshold from 8 hours to 2 hours, we would have more failures, but we are not sure if that classification is enough.
Was there some recommendation like 10,000 would be good enough, or?
We didn't do that analysis
Okay,
yet.
yeah, thank you.
Would mocking or simulating failures be kind of way to increase the size of the database or the data set you have to train the model?
We need to know then, so it's like chicken and egg problem. We need to know what causes failures. In Kubernetes there are thousands of metrics, hundreds of alerts, so we ourselves don't know exactly what can cause the upgrade failure. So data augmentation is possible, but we need to think really carefully that we don't synthesize the data incorrectly. So yeah, that's a good idea.
What was the reaction of your basically manager when you solved the 3 lines of code?
The manager is here.
Do you want to?
I think the reaction was.
Now the manager perspective. Yeah, so we still treat it as a success story because we've learned a lot. We learned a lot about the data. We found out the trade-off about perfection versus speed, and we have several leads to make it. So we hope next DevConf will be how we finally switch to machine learning. Thank you. Thanks for the attention.
Hello everyone, it's a pleasure to see all the people that came to the talk. So today we'll be discussing an OpenShift cluster deployed on one bare metal server. My name is Tatiana and I work at Red Hat France at Telco SA Partners team. I participate in two activities. Mainly, I actively contribute to distributed CI tool, which is a very powerful CI written in Ansible, and we use it to install OpenShift on bare metal. And I also collaborate a lot with Red Hat Telco partners on their real-life 5G workloads. So it's basically to help them to install OpenShift on their private labs, to install the workload, to help them pass the tests and certify, and automate all this using DCI. So here is the agenda of today's presentation. In 2 words, we will be addressing some pretty niche use case, which is really often in practice. This use case lies right in between the local OpenShift distributions and the enterprise solution with the clusters on many physical nodes. So it's something that you really often see in practice, then your application is too large to be fully tested on the local OpenShift distribution with one node, but is not ready enough to go to the full cluster, and we have a hardware shortage. So we'll be discussing this problem in more details in 5 minutes. I will be proposing the solution to this problem to deploy OpenShift on one but large bare metal server. And we will be going through all the hardware requirements, what will be created, and then we will move to how exactly do it. I will again show you how easy and seamlessly it can be done with DCI, and I will show you some demo, a bit accelerated, no worries here. And then we will move right in the conclusion. So that's the plan for today. Let's really start from the motivation. As I told you, the problem is really often in practice. So we work with telco partners, we see that a lot. So usually a 5G application is not something small. It's usually something really demanding. You can see a lot of situations that you need at least 2 workers running because of some particularity of the traffic, because of some situations with the application design itself. So you're not really in the situation and you could test the application on the local distribution. So you really need something pretty decent. On the other side, again, it's a telco use case, but you could imagine here any application which requires a particular hardware. For telco, it's often, for example, SRID cards, some security requirements, some data protection, which they are not yet compliant on the test stage. So there's something that imposes you to test this large application in-house. And as usual nowadays, you have a shortage of available hardware, so you just have one bare metal server, and you have basically a choice. You can wait while other servers will arrive and you could start testing, or you could maybe do something with one bare metal server that you have right now. So that is actually the solution that I'm going to discuss during this talk. So what we are going to do, like in general. So we are going to deploy our OpenShift cluster on fully virtual cluster. So what does it mean fully virtual? It means that we will be creating the nodes of OpenShift as virtual machines, and we will be connecting these virtual machines by virtual networks. All this we will be doing using Reviewed Libraries API, and all this will run on one single bare metal server. So all virtual machines and all virtual networks will be in server solution. So I just want to emphasize that since the beginning, all this is in servers. So VMs are in server and networks as well. So it's nothing like you really have to do a complex job with switches and network setup. No, all this is in server, and all this will be running, will be spawned up by simple Ansible playbook and will be destroyed the same way. So it's really convenient and simple solution here. So let's start right from the beginning. So we'll be first discussing our hardware requirements. Okay, so we'll be running on one bare metal server, but how large the server should be. So what do we need from the point of view of hardware, and which cluster from nodes point of view we could get in here. So here I'd like really to provide you two examples hitting in two extreme test cases. One is both are real life situations, okay? So all this is tested, it's not a theory, all this is running. So here you have sort of real life example for a large application on enterprise level. So it's not a cheap solution. You can see that it's almost 150 gigabyte of RAM here. So it's really expensive. It's a really enterprise solution, and this is what is running on the lab of one of our partners. Basically, the problem here is with the workers. You see, every worker has to get 32 gigabyte of RAM and 32 vCPUs, and that is really something that is requirement of the application. The application is pretty heavy. It works with 5G traffic in very particular way. So that is really the bare minimum requirement for the tests that we want to run in this lab. So this example basically shows you that even within one bare metal server, you still can get a pretty decent level of testing and pretty high level of confidence with what you're going to. So that's one example. But okay, it's really expensive. You see how many RAM, it's really enterprise lab. Maybe you have a home lab, or you have a simple solution, or you want to try it without really spending all the money. So I'm providing a second example. Again, it's tested and practiced. So what you can run. Again, I'm providing you the exact hardware in case if you'd like to try it on your own, if you have your home lab or something. So here again we have two workers, but this time the workers are much more decent, so they are really more smooth, they are more, let's say they are more slim, and you have just 8 gigabyte of RAM and 8 vCPUs per worker, but still you have two workers. So it's an example of the application that could really go on the minimum resources, but just requires somehow a bit more distributed. So this is what you can do in your basically home lab, like 56 gigabyte of RAM. It's pretty decent. In real life, to be honest, we are running it on 70 gigabyte, but still it's tested. We see that we really could go with this solution, not only on really expensive, on huge servers, but on small home server as well. So here we just discussed basically the nodes. We discussed what we are going to get as emissions that will be running on our cluster, but we also need to discuss one last step, how we will be connecting these machines in between. So we really need to create some networks that will be connecting our virtual machines that we created on the server. So again, I want to emphasize it again, it's in-server networks. These are networks created with Liquid APIs, so it's not like something that you have to do setting up switches and so on. It's something that will be done for you by Liquid API, and we will be creating two networks. So one is provisioning network. We will be using OCP API installer here, so it will be used to bootstrap VMs. And the second network is bare metal network, which will be used to connect all the nodes. Bare metal network here is in red. And you see that we will be automatically creating a router for external NATed connection. So basically your server will have some sort of outside connectivity, so you will get the possibility to go from your cluster to outside. You will not have possibility with this setup to go from outside to the cluster, but this is fine. This is testing setup. It's even sort of additional protection for you. situation. So bare metal network will also provide a basic DHCP and the DNS config, and every VM will get an IP address from DHCP pool. So we discussed what we are going to create. We are going to create nodes as VMs, and we are going to create 2 virtual networks that will be connecting these nodes. So the next question is how to do it. Here, again, it's a time for some advertisement of distributed CI tools. So here you have a DCI logo. And as before, it's really a powerful tool which is combining the goodies of CI with the goodies of Ansible. So it's CI that could do everything Ansible can. You could install OpenShift on bare metal, you could install your workloads, you can do whatever you want as you are working with Ansible, and you can do whatever you want as it's CI. So it's really the good things from both worlds united together, so it's really cool. So what we do, we deploy OpenShift, automate the deployment of workload, run various tests, and even propose the certification out of box. So it's nice. I like this tool for sure. I'm using it every day, and it offers a lot of flexibility. So here we will be using DCI in 2 steps. First step will be to create the whole virtual cluster that I discussed right before, virtual machines and networks. And all this will be done in 1 step. So we'll be basically just running one Ansible playbook until we'll be creating everything. It will be creating both nodes, networks, routers, everything. So you'll get fully pretty ready virtual cluster. And then the second thing, we will be choosing the OCP version to deploy this cluster, and we will be running API installer, which is available out of DCI. I probably did not mention, out of DCI we have basically all installers available, UPI, API, BI, AI. So here, for the sake of the presentation, I'm just using the API, but it's not the limitation. We have a lot of stuff available. Let's go to the requirements. So what you will need to install from software point of view. So you'll need to get Red Hat Enterprise Linux just to get all of your dependencies to be coherent. You simply install DCI, it's with DNF install, it's easy to do. And then the important thing here is to enable nested KVM on the jump host on your own bare metal server. Why would you need a nested KVM? This is a particular moment, but this is important one, so let me spend some minute on that. So we will be using OCP API then. So you see here we have a provisioner machine, and you probably know that OCP API works starting from creating a bootstrap VM. Since provisioner is already VM, and bootstrap VM will be created within VM. This way we will be creating VM within VM. So what we need here is really enable nested KVM for the sake of make this setup working. So here it's a really important moment. Not all hardware allows that, but nowadays most of stuff have this opportunity. So this is one of the requirements. We will need nested KVM to make this solution working. So now that's all about the dependencies, and we are ready really to go more into this tab. So we are ready to really go into the customization. So what I'm showing you here is not something that you have to write from scratch. The template is available within the DCI. You have a lot of samples and examples. So basically what you will have to do is that you will have to take this template, which is already here in various combinations. You will have a lot of comments and a lot of various situations that already thought about. What you will have to do, you will have just to take this template and customize it to provide description of your cluster that we just discussed before. So essentially to provide the description of your networks and to provide the description of your hosts. On this slide you see the part 1, which is addressing mainly the networks. And you are providing here the addresses for apps, API, DNS, VIP, so all standard stuff you have in here. And here are our two networks. So you see you have bare metal, you have this DHCP range in which you will have your APIs allocated, and you have this NATed mode for the outside connection. Okay. And then you will get a provisioning network, which is will be used basically for VMs bootstrapping. Then another part of the setup, here you have hosts. Okay, so here you start to describe really node by node what will be happening here. So here I'm really emphasizing the network part. So for every node, you are precising to which networks this node will be connected. So here I'm providing provisioning and bare metal, and just check it out. It's a nice feature for bare metal network. I'm precising here MAC. It's not mandatory, but it's a nice feature because then you could basically pin your MAC address in the bare metal network, and it's really easy to debug if you do further application debug. It's not like every time you assign arbitrary MAC address. It's really pinned here, and it's a nice feature, I think. So that's about the networks. The second part is, yes, we have to describe the nodes. As we discussed before, there will be some trade-offs between how much you want to spend on the lab and how much you can get in terms of RAM and CPU. And basically, once you decided this, once you created a nice table with your setup, what you need to do is just to customize the memory, the CPU, the disk size. You could also, it's not, I did not show it here, you could also add a second disk for the storage, for example, for the workers, if you have some stuff for the application. So, and for sure use KVM driver as a base. So that's what you will be doing, not just for provision cost, but basically for all the nodes. So you really customize node by node. You can make worker 1 differ from worker 2, and you can do anything you need. Again, I want to say that it's coming out from templates. So basically what you have to write here is just some numbers. It's not like you're running this whole YAML file from scratch. It's, you are basically taking whatever is already here and you are customizing the template. So now what we essentially prepared, we prepared our Ansible inventories. So I told you that DCI is written in Ansible, so this YAML file describing the cluster, that was our inventories. So what we are going to do, we are going to create our virtual cluster with just one command. So we will be running Ansible playbook, taking playbook libvirt up, and providing an inventory with the description of all nodes and networks. So what this playbook will be doing, it will be creating all the nodes, provisioning node, free masters to workers to networks, provisioning and bare metal. And it will also do one nice thing for us. It will generate the hosts file to be used later for OCP API installation. So it will be just creating the cluster, everything from scratch, and it will be also generating the description of this cluster in the form which is understandable by API installer later. And here is the demo. I hope that video will work. Let me try it out. So basically, this is a bit accelerated installation. In real life, it takes about 10 minutes. So what this part is doing, it's creating from scratch this virtual cluster. So what I'm showing you here is this inventories file, and I'm just going through all the nodes. You see, it's not too large. So once I customize the inventory, I'm firing my Ansible playbook. And now here it's accelerated in 5 times, so we will really installing the, our virtual cluster here is in 2 minutes. So again, what it will be doing, it will be creating all the nodes, it will be creating all the networks, and it will be generating a hosts file that will be used later for OCP API installation. Here I'm going to cheat a bit and move right in the end of the installation, just to show you how it will go. So let me just move again. So here, what you see, sorry for that. So I really wanted to come to this part. Then the cluster is already installed, and I'm showing you what was finally created. So here you see with this command I'm highlighting the nodes that were created, and I'm highlighting the networks and the host file. So it was a bit too short, so I think I'm going to do it a bit in more details on the next slide. It's running the video, so. I think they are good. So here is basically the screenshots from the previous output, just to check them out a bit more carefully. So here you have list of all the nodes created. You see provision host running, and the other nodes which are shut off for the moment, they will be powered on during the OCP installation later. And we have the networks. Again, these are in-server networks. You see they were automatically created by the playbook, and they could be automatically destroyed the same way without doing no harm and without messing up with your network. Also, it's an important thing, since we are using the netted connection to outside, it's pretty safe, so you will not mess up by adding this additional DHCP server. You will be just safe, you will be within your cluster. You could only go outside, and nobody will come from outside to your cluster to take IP address. There will be no mess up. It's a safe network config, and it's really nice from this point of view. So you have two networks, but they are safe, they are within the cluster. It's really cool from this point of view. So now what? We have our virtual cluster. We need now to run the last step. We need to deploy an OpenShift on that cluster. So what we do now, so we essentially will need 3 files. So the hosts file, which is description of our cluster for OCP API, is already generated by DCI playbook libvirtual. Config is a file if you need to add some DCI configurations to get it displayed in DCI UI. It's basically a way to nicely display all Ansible logs at once. We do it with our partners basically to share the installation and to help them with the debug. And the only thing you have to customize really is settings. As before, settings is a template, and you don't have to write it on your own, you just have to trim some things. Here you could just provide the name of your lab, to provide the information that you are installing in OpenShift, and to choose the OCP version to install. So here I'm choosing 4.12, and that's enough. So all this stuff, half of it is already generated for you. You choose the OCP version, and you fire the installation using DCI CTL. DCI CTL we installed before with DNF package, so all this is pretty straightforward. So I'm not showing you a demo of OpenShift API installation. It's 40 minutes. It's just a standard API installation. It will not add a lot of value here. What I want you to show is the final result. I want you to show how it turned out to be. So we get our cluster installed on our virtual cluster. You see here we chose 4.12 OpenShift, so it's 1.25 Kubernetes. And to interact with the cluster, DCI already generated for you the special folder, cluster configs, in which you have all required binaries. And you have kubeconfig to interact with your cluster. So you have everything in one folder generated during the API installation out of DCI. So here is what you got finally. These are the same nodes that we've seen like several slides before as a virtual cluster, and we have our free masters and free workers and running. So that's pretty much it. So I want again to emphasize that we're addressing some sort of this gap situation, which is really often in practice. Then we do not, then we have application which is large enough to and can't fit in the tests with the local OCP distributions. But we don't have enough hardware or enough budget or enough readiness to already build this full enterprise cluster with many nodes. So this pretty niche problem is pretty often, and what we propose here is to fill this gap by instantiating for testing the solution of OCP on virtual cluster. Again, I want to emphasize here it's not a production-ready solution. It's not something that will give you the best performance and stuff. Some of our partners, they are still running some basic performance tests, to be honest, but it's not something that you want to really do. It's mostly a testing solution. It's not production-ready solution in many senses, but it just allows you to start testing more quickly, and it also allows you to start some testing just having one server. And yeah, I want to also add a bit of advertisement of DCI tool here, which we work on our team. So it's a really nice tool. It's CI written in Ansible. It can allow you to do a lot of things out of box. I invite you to check it out. It's quite nice tool. We are really open to the contributions if you'd like to try it out. If you have some particular test cases, we are really open to the community needs, and we're actively working with 5G telco partners, so the tool is really evolving really fast, and it includes a lot of new installers, a lot of new possibilities. We're constantly evolving, we're working a lot on the tests. So it's really nice and good OpenShift community. So here I'm providing you all the links, just in case if you'd like to check it out. So concerning this talk, OCP cluster on repeat, I'm providing you a source code of Ansible role that I just used because maybe you would like to check in technical details exactly how it was done. I also provide you a link to configuration templates and samples if you'd like to try it out. So you maybe would like to check ready solutions out of box and just customize them. And here is blog post on this topic, so if you want to get this talk, but in more technical details, like really with the whole configuration out of box, with the whole discussion, just check it out. You will see it's the way more extended here, a bit limited in time, so check it out. And here some information about DCI if you'd like to get started, so it's introduction, documentation, and we also have a nice blog that we are trying to keep up to date. We are regularly writing the articles. Don't hesitate to check it out. And thank you so much. So I think we have 2 minutes for the questions.
Questions?
Don't hesitate. Let me just
I have a question about the lasted VM.
Yes.
Can we provide the DHCP, bootstrap DHCP service by the provisional VM directly?
Yes, basically that's what we do here. We have basically two DHCP. We have one DHCP for provisioning and one DHCP for bare metal. So you have them right here.
I mean, can we provide the DHCP directly by the provisioner, not the lasted VM?
You mean you want to provide DHCP for bare metal network then?
No.
Is that correct? I'm just trying to understand what is the need. You already have DHCP on your cluster and want to use it both for in-cluster connectivity and for IPs of VM.
Understand.
Yes, you can. It will be a bit more challenging for you in the sense that in this situation you see you have router and you have the external connectivity managed through. If you already have DHCP here, probably it will be exposed to outside network. So in this case, you are not protected for the situations then, for example, some machines from outside could come to your server and get IP addresses out of there. That's one of the setup I did in the past, and it was really painful because we nuke out basically the entire lab of the partner. So I do not recommend this, but you can definitely do it. It's just that you need to be a bit more proficient in network setup in this case.
As I know, the nested VM is not officially supported. It's just in technical preview. I'm not sure.
You mean the possibility to enable nested key VM?
Yeah.
This you will need anyway if you use API setup. If you use OCP API. So yes, it's not a recommended production setup. I always emphasize here it's testing stuff. There are a lot of things that are not really supported on the production level. So it's just starting from libvirt API, to be honest. Libvirt API is not something that you will run in the production having the full support. So yes, it's a testing setup.
But it can also be a solution for the customer, right?
What do you mean?
Since
to not use nested key VM?
I mean, you have mentioned that this is a solution for the 5G tech case. So I guess it's a solution for customer, right?
Yes. Yes, it's a solution for large 5G workload for the testing, yes.
So even it's in technical
Very good.
Yeah, but do not hesitate to come later. We could discuss in more details. I see that you are hands-on the solution, so maybe I will provide you more details on your particular case.
Any more questions?
Any other questions?
So the installer controls, provisions the nodes via IPMI or Redfish, if I understand correctly. How do you provide the IPMI Redfish interface to the VMs?
We are not using Redfish here, we are using VBMS. But there are some solutions with Redfish. You could check with one of my colleagues, I will give you contact. Any other questions?
Okay, so let's thank the speaker again.
Perfect. So last session of the day. Thank you for making it. You deserve probably an extra beer tonight. Plus it's very hot. Well, I mean outside, inside is not too hot. So the session for today is going to be about Kubernetes CI/CD pipelines for containerized databases. So the topic we're going to be touching on are Kubernetes. So what is a Kubernetes pipeline? It's a pipeline run entirely inside Kubernetes, and for this we're going to talk about Tekton. Who's familiar with Tekton? No one, or a little bit, so we're going to talk about it. We're going to see two types of pipeline. One more for who is a developer? Okay, some of you. So more of a dev pipeline. How do I work with databases in this pipeline if I want to change things? How can I combine this with the rest of my application? And and the rest is Tekton, as I said, containerized databases. Who is a DB admin? I don't know if that job exists anymore. I'm always asking, and I never have like any hands up. So yeah, we're gonna see why. I mean, is it a good idea or not to run a container in databases? And we're gonna talk a little bit about the differences between deployment and stateful sets. Who knows Kubernetes already? Who's familiar with the concepts? A little bit. We're going to touch on this at the beginning just to set the stage. So my name is Nick. I'm a dev. I'm the head of. I'm heading the DevRel team at Spectral Cloud. I've been working with Kubernetes for the last 6 years. Doesn't make me younger. Both on the CNI, so more network side, when I was at Cisco, and CSI. I worked for a company called OnDat or StorageOS. I don't know if anyone is familiar with this. It's distributed storage for Kubernetes, essentially. So let's get started. First, just to set the stage, if you were to run a database, what are the basic constructs you would use in Kubernetes? So you have two choices. Typically, Kubernetes run, I'm happy to have this now. I don't have to point, this is magic. So typically in Kubernetes, you're running pods. So pods can have one or more containers, and those pods in Kubernetes are controlled by a controller, the high-level controller that, if the pods fails, it's reprovision it, just to make sure the right number of pod or the desired number of pod is running. So we have two types. We have deployment and we have stateful set. Deployment is stateless container, or often referred as cattle. You don't care about it. They don't have any stable identity. If one pod is dead, then another one will be restarted with another DNS name, another IP address, all of that. Deployment have interesting properties in the sense that when you define a PVC in Kubernetes, this is I want to attach a volume to my pods. I want to store data in my pod. When you have more than one pod, right, they all share, you define the deployment, you define one PVC, and they all share that particular definition. Which means that if you run a PVC in a traditional access mode, which is read-write once, not an NFS share or anything, something like locally to your disk. What that means, it means that the first pod will claim it, will own it, but the other one will try to write inside this one, but it won't be possible. Only the first one will be able to write in this volume. So what that means is that if you need multiple pods to get access to the same volume, then you need something like an NFS share and run read-write many access mode, right? This is the only way to make a deployment work with multiple pods who need to access the same data, right? That's stateless, which means that PVC, first off, is the only way for the data to persist. So if you create a deployment and want the pod to have stateful data, you have to use PVC. If it's a deployment PVC, multiple pods, then you need an NFS share, which is probably out of the question for a database. And that's the point what I'm trying to show here, is that if you're running a database, then it's probably a better idea to use stateful set, because what you need is a stable identity, especially if you're building a cluster of database, right? Here, imagine this is a database cluster where every pod is one member of that cluster. The difference between stateful set and deployment is part of the declaration of your configuration, so the YAML file. Inside a stateful set, you have, on a per pod basis, you have one instance of PVC as opposed to a single one here. So what that means is that every pod has its own storage volume, own storage capacity, can write uniquely at once, RWO, read write once, into that particular PVC. So that's one reason you want to run stateful sets. As I said, the second one is because when this pod dies, so the stateful set controller will reprovision this pod with exactly the same ID, exactly the same DNS name, and exactly the same pod name as well, right? So it's really the way to provide a stable identity inside Kubernetes. Anything that is stateful in Kubernetes should run in a stateful set. That's the basic rule, right? So bear this in mind for the rest of the conversation. This is what that means. Stateless, deployment, stateful set, hence the name stateful set. Okay, but at the same time, if you want to run a database into the new world of cloud native, you inherit those properties like scalability, elasticity, self-healing, observability. All of that is great for its new qualities, new features for your databases, because they inherently inherit this from Kubernetes, because this is what the platform provides. But when you run a database from, you go from a SAN or like a big array, you still need the enterprise feature that were provisioned with this array. This is why I ask, who is a DBA? Because DBA know that you need replication, you need the system to be distributed, you may need encryption. Eventually, because we are in cloud native, you may need self-provisioning and be DevOps friendly, right? So all those features are not, at least the first three ones, they're not inside Kubernetes. And this is the other part when running stateful set, you have to ask yourself this question. How do I provide this inside Kubernetes? And the answer is via the CSI, the Container Storage Interface. Again, Kubernetes just provides the interface for your storage features. So depending on the CSI, so you have StorageOS, Ceph, Portworx, all those companies that provide these extra features from the particular CSI, right? So be careful of the CSI you use, especially in production where you need things like encryption for the databases, replication, all of that. Of course, you may have duplicated function in the sense that the database itself can provide replication, but remember, if you lose your pod, you're going to start from an empty PVC, right? So you will need to replicate from nothing up to all your data. If you do storage-based replication, when you're going to restart your failed pod, you only have to replicate the delta, right? So that's the main difference why you need hardware-based replication and, let's say, software-based replication or replication from the database itself. Okay, another reason, for people who are asking, should I run a database inside Kubernetes? Well, this is from Datadog report that the top is listing the top technologies running on containers. And you can see that Redis, Postgres, Elastic, Kafka, Rabbit, Mongo, MySQL, and Vault, all of that are stateful workloads, right? So obviously, they are running in containers. So what that means is that already, even before Kubernetes, those technologies were popular to run in containers. So now the top containers image running in Kubernetes stateful sets, again, you find exactly the same ones. So what does that mean is that people who are running those technology, they do it in a stateful set. So definitely stateful set is the way to go, but it's not the only thing. So what we've seen so far is just the database, storage, the capacity, the features, but how about the application layer? How do you install the database? Because if you have your database controlled, the pods controlled by a stateful set, okay, it's going to maintain a certain number of pods. It can, do rolling updates, all those things. But how about what is running inside those containers? How do you make sure that the database is installed properly, the cluster is installed properly? How do you monitor this? Well, by using operators. So who is familiar with operators? Some of you. So let me explain for the others what an operator is inside Kubernetes. So Kubernetes is basically an extensible API. Right? right? So every object inside Kubernetes lives within this API space. So you will find things like pod, daemon sets, stateful sets, all of these exist as first-class citizens inside Kubernetes. But there's no such things as MongoDB inside, as an object inside Kubernetes. And the idea of the operator is to create what we call a custom resource definition, which will make MongoDB first-class citizen inside Kubernetes, so that Kubernetes now knows what a MongoDB is. And that's the first part. That's the API definition. I'm extending the Kubernetes API to make Kubernetes aware of what a MongoDB is. Then the second part is a custom resource. So it's an instance of that particular object definition. So it's basically a YAML file, the same way you create a pod or a service or a secret, you can create a MongoDB cluster, right, by respecting the particular syntax that you have set in the CRD. And then the third part is the custom controller. So the custom controller, you can think about it as a runtime environment that manages your custom application. In our particular case, we've extended Kubernetes with CRD MongoDB. The role of this runtime is to make sure that whatever I do as a custom resource, the controller watches for the create, update, delete operation on that one. It takes appropriate action to make your desired state living inside Kubernetes. So if I create a MongoDB resource as a custom resource here, as a YAML file, the custom controller makes sure that everything I mentioned in this custom resource will be living in the cluster. So creating basically this application layer, installing MongoDB, making the right number of nodes inside the cluster, making sure sometimes providing backup capabilities, all of that is encapsulated into the custom resource for the definition, and inside the customer controller logic that will perform all the automation, right? So all of that is what we call an operator. So it's the custom controller, the custom resource, and the custom resource definition. So now we have three things, right? We have the operator, we have the stateful set, and we have the CSI. Those are the three components you need to think about when deploying databases inside Kubernetes. So you don't have to build this yourself, right? The operator, you can find your preferred vendor. Like Mongo, they have enterprise, they have community operators. There is company out there that specialize in building operators. For etcd, there's the improbable operators. If you go on operatorhub.io, you will find all the possible operators to manage pretty much everything from Redis, MongoDB, and even non-stateful application. But yeah, that's the third part. So today we're going to see the Marvel app, which is an app I've built for to demonstrate MongoDB and to build a full application on top of this and create some CI pipeline. If you go on this link, you will see I've got a full 3-part blog if you want to replicate the same configuration at home. Okay, so this application profile is that one. So if we start with the top, we have multiple front end. I know Flask is supposed to be a backend, but it's exposing HTML by using the Bootstrap plugin in Flask. Then I have a 3-node MongoDB cluster that is deployed. MongoDB is deployed as a stateful set, inheriting from the storage class. So the storage class, this is basically how you map the CSI to your stateful set. So the CSI layer, like all the features, are controlled via the storage class. So if you want to enable things like replication and encryption, is by using a storage class that has this enabled, and then you say for the stateful set, oh, by the way, use that particular storage class. This is how you make the link between your PVC, your volumes, and the storage feature set you want to expose for your database, right? And then, so this is typically what you do in a stateful set. Stateful set, you configure a volume claim template, you associate a storage class, and then you say, I want, when you deploy a pod controlled by a stateful set, it will have an individual PVC, as we seen in the beginning, as opposed to the deployment, right? So one per pod, individual PVC, all enabled with the feature that is sitting there, right? And the role, this application, what it's doing, actually the front-end Flask application is going to pull Marvel character from the Marvel APIs, store them into a MongoDB databases, and display some random cards containing the Marvel character information, right? So this is the pipeline that we are going to run, but essentially it's two different pipelines. The first one, I will show it live. The second one, as I said, I messed up, so I will show you the video. But the first one, which is on my laptop, right? How do I control the pipeline on my laptop if I want to develop my application and change code live, for example? So what we are going to do is, so we have our application code stored in Git repository. Then, of course, we have Docker Hub. We're going to build images, publish them to Docker Hub. And we're going to use Customize as a way to deploy the manifest into our cluster. So who is familiar with Customize? A little bit? So Customize basically take raw manifest and apply some customization. For example, you could say, I'm in my dev environment, and because Mongo is now a native resource in Kubernetes, you can control things like the size, right? The number of nodes. So you could say, locally, please deploy only MongoDB on one node, and I just need 1 gig of space, right? Now, when you go to the production, let's say pipeline, things get a bit more complicated, right? So we're going to be using a tool called Scaffold to build our images. It's like, you can think about it as Docker Compose, but for Kubernetes. It's helping building application, building containers, and running custom Docker build commands, right? For production, we're going to push our code into a Git repository. Then a Tekton pipeline should be triggered, but I'm going to do it manually in the video. So Tekton is a pipeline, the same way like Scaffold will be doing the pipeline bit locally on your laptop. Tekton is going to do it inside Kubernetes. And every task, every step of the Tekton pipeline will be a container, will be a task that runs as a container. So everything will be running in Kubernetes. And the task of Tekton will be, again, build the image, build the manifest with Customize, publish the customized manifest on the Git repository that is monitored by Flux. Who is familiar with Flux? So Flux is a GitOps tool that allows you to monitor Git repository, and anything that is published in this repository will be deployed in Kubernetes. So why should you do that? Because it's more secure. You don't want to deploy to production using kubectl, like here. I mean, Scaffold will be doing the deployment, but using kubectl. In production, don't do kubectl, it's bad, right? Do you have any experience with this? So typically, the manifest, you publish them somewhere as a Helm chart. I mean, there's a variety of things you can do, but for the sake of simplicity today, we're just going to publish raw manifest from Customize, run as a task in Tekton, and Flux will be monitoring the repo. As soon as the manifests get uploaded into that repo, Flux will provision all the manifests into the cluster, but this time with different properties, right? We will have a 3-node databases, we may need more storage, and we may enable encryption, replication, deduplication, all those kind of things, just by changing things with Customize, using Customize here and here. You have the same base manifests, and then you can tweak a little bit of, you can patch the manifest, saying I want this amount of storage, or I want, that many nodes, I want replication. Actually, you have all the features there. Replication, encryption, and this only one replica or no replica at all, right? Just by using Customize different patches. Okay, so let's go for the demo. It's been, what, 20 minutes? So we have
10 minutes.
10 minutes. That should be enough. So, yeah, let's see. Okay, so let's go here. So I'm going to show you live the scaffold part. So scaffold, again, very simple syntax. Here I'm using a name, the image I want to build, the Docker image, the name for the artifact, the context, the Docker build context, and a build command. So typically you don't need a build command, but I'm using an M1, so I'm using ARM, so I need to use Docker build X to cross compile, right? This is why I need this script, but you can just use native Docker if you're running on x86, right? Local push through means that I want to push the image to my local Docker daemon as well. And here, this is the path to customize. So you can see I have my dev overlay. So in customize, the overlay is the patching. What do I need to change to apply this in my yeah. So for example, for Mongo, this is my overlay, and I say I need only one member. Like for example here, and I think the storage is 2 gig. Right? So this is, in production I will have something different. I don't have it here because it will be built by my Tecton pipeline. So my Tecton pipeline is going to build my my customized manifest as well. So it's just to show you there, like, with customized, depending on the environment, you can easily deploy depending on your needs. Okay, so this is basically what you need. And then scaffold can run in multiple modes. You can do scaffold build, scaffold run. So here I'm just making sure that I'm running in my development environment, which is this Kubernetes cluster. We're going to be using K9s. So I don't know if you guys are familiar with K9s, but it's probably one of the best tools to monitor and to do any sort of operation in Kubernetes. So this is my current cluster, let's say my development cluster. And Scaffold is going to create a new namespace called dev and deploy everything into that namespace. So for this, I could do scaffold build, but what I want to do is also change my code live. So as soon as I change the code, I hit save, and everything is getting deployed again into my cluster with the updated code. So I don't have to go through the whole Docker build manually, update the image, and redeploy. This is this feature I want to show you today. So if I do scaffold dev, so it's going to build the image, and then it's going to start the deployment, and it's going to log all the container logs. So you can see the logs live from here. So this is my Flask mobile app. This is my front end. And if you see now in K9s, there is a new namespace called dev. And you can see that the Marvel front end is deploying. So in customized, I've chosen 3. In prod, I think I have 5. And MongoDB, 1 single instance. So the operator, remember, is controlling how I should deploy MongoDB. So the operator is now deploying the MongoDB database. And the add data is just like the job that is going to pull all the API information from Marvel and store them in Mongo. So it should fail because the first time, it's a job, so it's going to repeat until it's successful, until the DB is ready. So this one is ready. So actually it should already be working. So yeah, you can see here, this is all the API request from the Marvel API. So now I should be able to test my application. So to test my application, still using K9s, I go to my service. I've got my front-end service. If you create just Shift F for port forward, I want to redirect this service to my local host. For 8080. So now I should be able, this is my Marvel application, so it's running. So you can see I'm going to make a quick change to show you the difference. It's commit, I want to add an S. So I'm going to go back here, I'm going to go just for my port forward. I'm going to delete the one I have. Okay. I'm going to go into my code. So you can see, if I go back here, I still see the logs, right? I go to my app, template, the page. I'm going to find, to look for a comic, and I'm going to replace by comics for all the instances, right? And then look, I'm going to save, hit Command S or Control S, and if it works, yeah, you can see, it's now rebuilding everything and redeploying everything. So now I should see new container coming. You can see 2 seconds. So it's changing, deleting the old one, creating the new ones. So now if I go to my service again, I'm again creating the pull forward. I go back here. So now my application has been updated. So you don't have, so the value here is you don't have to rebuild. You've probably saved, I don't know, 5 minutes from building everything. Imagine, you know, if you have to change the code hundreds of times a day, that's 100 times 10 minutes you're saving, right? So that's for your local laptop. Then I'm going to move to the second part. 5 minutes, right?
5 minutes.
Okay, that's perfect on timing.
Actually 10 if you want to take it serious.
Yeah, it's fine.
So
So I'm just sorry, like I messed up my cluster, so I'm missing some storage class, so I have to use my backup video. But I'm just gonna show you what I'm doing here. So same principle, I'm gonna use Tekton. So Tekton is basically, you create, I'm not gonna explain every concept, but Tekton has, you run pipelines. Pipelines are composed of tasks, and normally I have 3 tasks. I have build Docker image, I have then use customize to create my customization file, and I have git command to upload the customized file into my repository. But I don't have that tasks here because Tekton has a marketplace where you can just use YAML file, apply them to your cluster with built-in tasks. The only thing you have to do is give some scripts. So for example, here I'm using the git task, and this is my git commands. And then Tekton just acts as a wrapper around my command. So the point is, there's a marketplace, it's very easy to use, even though the structure is kind of not complicated, but as everything you have to get your head around it. But then for every task, you can either build your own or use one from the marketplace. So pipelines are composed of tasks. Tasks are using resources, and then you have the pipeline run. So basically, as everything in Kubernetes, you trigger the Tekton pipeline by applying the pipeline run manifest, which is what I'm doing here. So I'm just creating, so kubectl creates pipeline, and I'm just going to monitor what's happening in the logs. So just by doing this, you're going to see it's going to trigger my first task as a container. So every task is going to be a container. And you can see within that container what's happening. So it's building the image. The same thing I've done with scaffold is doing this. And by using the tkn pipeline logs command, it's displaying the same thing as what is happening here. So you have 2 choices. Either you use the tkn command to see the logs of all the tasks, or you can use every container, so it's still building, you can use every container that's for every task, go into that container and display the logs as well. The difference is here, it's everything in a single place. So here, still building the image, downloading, the required, the mypip requirement.txt. So really building the image from scratch and pushing it into my upstream repo, registry, sorry. Right, and now, so you can see this task is done. Now I'm moving to another task, which is building the customized manifest. So again, I'm logging to that container, and what is here is exactly the same as here. Now it's done with that, I believe, so customized manifest. I think it should be done very soon. Third one. So the third one is basically the pushing the manifest using my Git from the marketplace, my Git task for the marketplace, and uploading this into my manifest repository then that Flux is monitoring. As soon as Flux, you can see, I'm monitoring, so Flux is monitoring. As soon as it sees that there is new manifest on the repo, you will see reconciling And as soon as it does reconciling, the manifest should be deployed into my Kubernetes cluster, but this time with the customization I've set up for my production environment. So that will be a 3-node MongoDB database, and I think I just put 1 gig of storage. But I mean, I need more storage in there than in production. Doesn't make sense, but it's just to show you that it's possible. So you can see, like, I have more front-end pods. I think I have 5. If I go back here, and you can see that the new revision, so the new manifests on the repo have been applied here. And you can see 1, 2, 3, 4, 5, and the 3 tasks from Tekton are now completed. So my deployment of my application is basically done. So the last step is basically, so you can see the MongoDB cluster is still deploying, so this time 3 node, taking a bit more time. So my job is going to fail probably once or twice. So, and you can see also the PVC have been deployed with 1 gig of storage, the first 6 ones, the data volume as well as the log volume. And I think that's the last bit. So yeah, you can go to the model front end now, and same thing. Now it's because it's running in a cloud, it does have an external IP. I don't have to redirect to my local host. So now the only thing that remains is basically doing the same thing, testing that the application is running and working with this public IP address, 8080, and yeah, it is now running. So, but it's easy, it was a video. So okay, so that was it for the demo. And yeah, that's pretty much the end of it. Key takeaways for today. So databases can happily be run as container, provided you have the right tooling in place. So you have to figure out the enterprise data features when migrating from SAN or NAS to Kubernetes. So we've seen you have to think about the CSI, you have to think about stateful set versus deployment. Of course, it's going to be stateful set, and you have to choose your CSI wisely and your operator wisely as well, and make sure that you are using the right pipeline tooling. So Scaffold is one example. I just did another lab on DevSpace, which is also a good alternative to Scaffold. For your main CI pipeline, it's up to you. I've shown Tekton because Tekton is Kubernetes, and we had Kubernetes in the title. It also allows you to repeat the same principle everywhere. So you can be on-prem, in Google, in Azure, in Oracle Cloud. As long as you have a Kubernetes cluster, you will be able to use Tekton rather than the individual cloud-specific, vendor-specific pipelines. And as I said, I'm part of Spectral Cloud. And if you want to run stateful applications in Spectral, actually, or even any cluster, what we do provide is layers that you can build and are repeatable in any cloud. Once you have your cluster profile defined, we provide things like backup, scanning, and all that using open source tool like Velero. So that's also another options. I mean, there's Spectral, but not only Spectral. If you run some cluster somewhere, you have to think about the backup. Right? That's another thing I didn't mention. There is replication, but you also need backups. So whether you use Velero, Spectral as the platform, which is using Velero, or Kasten, Kasten, they also have other solutions. There are operators that also provide backup solution, but also think about your backup. And that's pretty much it for today. Do you have, yeah, thank you. Do you have any questions?
We have like a minute, so one, two questions.
Maybe online, I don't know if they can ask a question online or...
They can, but there was...
Yeah, people kind of didn't figure out that there's this thing on Matrix they can ask questions at.
Oh,
so,
okay.
Like, I haven't seen anybody use it yet.
Yeah.
Throughout the entire...
Okay, so did everyone get it? Right? I'm just yeah, it was understandable, so yeah. Thank you. So I guess you're free to go, guys. Thank you.
Thank you.